Good morning, everyone. Can you hear me, Francesca? Is that okay? Just a second, I can't hear you. No, I think it's okay. You are muted. The second. The Conforma conference. That's the first day of the conference, and it's the tutorials day. So I'm Michele de Souza from Centro Universitário FEI, and it's my pleasure to welcome you to the SBMicro 2022 Tutorials Day. It's organized by Electron Devices Society as a mini-colloquium, and organized by FEI Electron Devices Student Chapter. Yes, Francesca, everything okay. So that's the program of our mini-colloquium. So we will have 4 very interesting. You hear me? Yes. So here now. We have 4 presentations, and we are starting with Francesca. And just before starting the first presentation, let me talk a little bit about Electron Devices Society. It sponsors several conferences, as some of them listed here, and they have several publications in the field of electron devices, and it provides networking, supporting over 140 chapters in the entire world, and it gives several awards and recognitions. Being a member of Electron Devices Society gives you access to free online publications and discounts on electron device conferences and publications, and several other benefits that can be found in these links listed here. So not taking more time, let's go to the first presentation. That is Augmented Silicon Technologies with Graphene, given by Francesca Jacob. Francesca received her Master in Physics from Roma La Sapienza University in Italy in 1996, and her PhD in Electrical Engineer Material Science from KUL in Belgium in 2004. She's currently Professor of Nanoelectronics in the Faculty of Engineering and RT of the University of Technology, Sydney in Australia, and Chief Investigator of the ARC Center of Excellence in Transformative Metal Optical Systems. She has over 20 years of research and development experience in semiconductor industry and academia. And her research focus is translation of basic scientific advances in nanomaterials and novel device concepts into industrial processes. Her seminal work at IMEC on low-K dielectrics for on-chip interconnects over the 1999 and 2009 decade has informed the industrial uptake of porous dielectrics into modern semiconductor microprocessors. She has a lot of achievements, a lot of awards. So with no more delay, I invite you to the stage, Francesca. And
good morning, Michele.
The stage is yours. Please come to one of the spots to have your...
Sure. There you go. Moving to the stage.
Oh, the stage is yours. Please feel free.
Good morning, everyone. Thanks, Michele, for the nice introduction. And I'd like to thank all of the organizers for this invitation. While I'm trying to share my screen here on the system and share my audio as well, and hopefully that will work. So Michele, can you just tell me if you can see my presentation now? Okay. I take that is a yes. So, again, good morning, Brazil. Bom dia no Brasil. Aqui está um pouco tarde. This is a little bit, we are on the other side of the world, so it's late on Monday. We are ahead of everyone else. And I am really glad to be here in this nice virtual conference to talk a little bit about our work in graphene, and particularly in the work we've done regarding graphene augmenting and so complementing silicon on silicon substrates. So, as Michelle already said, I am nowadays professor down under in Sydney at the University of Technology Sydney, which is, for some of you may have been in Sydney already. So this is Sydney downtown, we call it CBD, and UTS is just very central here, very central campus. So if you ever have the opportunity to come to Sydney, please do let me know. I'll be really glad to host you for a visit and potentially a seminar. I won't talk too much about the Electron Devices Society because Michelle has already given a very good introduction. I just remind particularly the students that is always a really good value for money being a member of EDS because of the access to all of the different capabilities, networking, and papers online, and discounts on conferences, and so on and so forth. So before I enter into the core of my presentation, I would like to make some acknowledgements, also because usually the acknowledgements otherwise stay at the very last minute, and I always have to really go very, very fast on that. So, of course, I'd like to thank all of my current and past group members. So I've been down under for the last 10 years, so there's been quite a few people going through. And the technology I'll be talking to you about and our learning based on that technology has been developed thanks to all of these people. So here are some pictures of my current members. But also, there's a lot of collaborators across the world that have been extremely important for us and to develop initially the basics of this platform, and later on more the applications of that which I really would like to share with you. So last but not least, we have been having a really solid collaboration with AFRL, so the US DoD, Air Force laboratories, naval laboratories, and as well as the Army. In Australia, we're supported by the Australian Research Council, which is our main funding body, the Defence Science and Technology Group, and various entities, institutions that give us access to synchrotron and other important microfabrication capabilities. So this is clearly something that I wanted to mention before starting. And then we can move a little bit to the outline of my talk. So I will start with graphene, of course, is a very big topic. We have a particular angle that we approached graphene from. And it's a very practical angle. I will explain to you a little bit later how they came to be. And so I will introduce a little bit in motivation, the fabrication principles, and the basic properties of this platform. Then I will move into the application areas. These are a few of the application areas that we are really looking into. I don't think I will be able to go in equal detail through all of that during the presentation, but I do want to give you some ideas, at least in probably a couple or maybe 3 of those. Let's see how we go with time. And then, of course, I'll get to summary and perspectives outlook from there. All right, so just to start, what was our angle? Of course, there was a lot of people working on graphene, a lot of people, contributing to different aspects of this really fantastic material, which is not necessarily always that easy to work with. However, one of the important things about graphene is that its very atypical properties are something that could really augment silicon technologies in quite a few different areas, few different aspects. And I'm mentioning a few, we're not necessarily working on all of them, but for example, for interconnects to thermal management, those are areas that are very important. Energy storage, photonics, optics, optical devices, biosensing, and see that I am particularly, I'm consciously leaving aside at the moment front-end devices, which is something that with the platform that we are, that I will share with you, is not something that we're looking into, but certainly a lot of this aspect we are. Now, our angle towards graphene was, as I said before, is a practical one. We wanted to have a graphene directly grown onto silicon substrates. And the main reason is that we believe that having graphene directly on silicon substrates will greatly simplify the integration of that material with silicon technologies, with the existing silicon technologies, and of course the very advanced logic that is already available on silicon. And particularly, this is where we're looking into, like making a 3D integration of different tiles of silicon, each of them with a different performance. And this type of combination where you have silicon tiles all doing different functions, complementary, for example, to logic, to memory and such, this is really very, very interesting. For example, see in the context of the Internet of Things, where you want to miniaturize all of your, not just the single chips, but the system as a whole. And we're definitely going towards the Internet of the bodies. Some of you may have heard that already. This is the next big thing after Internet of Things. And the Internet of the bodies basically means that's a time where basically electronics and humans are kind of merging in a way, okay? But I don't see it as a threatening thing. This is something that really will help us to, you know, to make up for, well, help people with diseases, but help people with impairments, but also making our daily life much easier. Okay, and there are some examples here, but I will talk about that a little bit later. And actually, particularly, I will talk about the way we are going to interact with electronics in general going forward may have a complete big shift. I will keep this for last. So we are going to talk to you about brain-machine interfaces. But I'm first going to start very, very broadly from there regarding a little bit graphene in the context, okay? What do I mean by that? As I said, graphene has been really heavily studied for more than a decade by now. We learned a lot about graphene and how it works. It does not mean that graphene, although it was the first 2D material kind of rediscovered, it doesn't mean that it's an old material yet, because there's still lots of new basic science that is coming to the light. And for example, the twistronics based on graphene is one aspect, relatively recent. And there's a lot of aspects that are not particularly completely known and completely describable by a unified theory regarding graphene. And this is one of the kind of controversial, made on purpose controversial papers that appeared on SES Nano a couple of years ago. And the idea was to basically emphasize the fact that although we think we know a lot about graphene, and we probably do, there's still a lot missing in terms of how graphene interacts with different ions and how we can describe this with a unified theory. Last but not least, another aspect of graphene one has to consider when getting into this field is nomenclature. So nomenclature and related characteristics. So of course, when we talk about material science is contributed by people that are in fields as different as physics, chemistry, engineering, and such. And each of us has a different starting nomenclature. So, and a different understanding about graphene. The understanding about graphene from a chemistry perspective is not necessarily what a physicist would have, and particularly the physicist would have the idea of the single monolayer graphene, freestanding in vacuum, not interacting with anything around it, which would show the maximum amount of extraordinary properties that we really attribute to graphene. The reality is that this is correct. This is correct from description point of view. However, when you put it into practice, it is almost never the case that you would use a freestanding graphene in vacuum. You would have to use it integrated. For example, for microelectronics, it would be surrounded by a lot of different materials. And so the idea of graphene properties may not translate directly, and probably will not translate directly, from the ideal properties that have been independently studied. So this is a very, very important point, and this will come over quite a few times during my talk, and it's something that I really wanted to emphasize, and particularly this sentence here is often misleading to talk about superlative properties of freestanding graphene for benefiting applications, because graphene will have to be combined with something else in order for those applications to actually come to light. All right, so that was an initial preamble. Now let's get a little bit more technical in terms of, okay, we're talking about microelectronics. How can we harness graphene for microelectronics? And I mentioned already, we would like to have graphene on silicon wafers. Historically, a lot of graphene work has been done by using flakes, which has really advanced the field very well. However, of course, as you can imagine, using flakes to cover large silicon wafers is not necessarily the most realistic way you can go about it. Even if you were able, and it's possible, to grow flakes that are large enough that can be transferred onto a silicon wafer, large as you want, the problem is probably going to be sooner or later reliability, and we're going to talk about that. So basically, this is clearly not an approach that we wanted to follow. We wanted to focus on epitaxially grown graphene. And in this area, there's been a lot of work for, as I said, over a decade of work into epitaxial graphene grown on silicon carbide wafers. Here are some early examples from different leading labs around the world. You can see we're talking about silicon carbide because silicon carbide is transparent, and these are examples of chips made with graphene onto silicon carbide wafers. So we know pretty well by now, people use different tweakings of this process, but basically the way that epitaxial graphene is grown onto hexagonal silicon carbide is by thermal decomposition of silicon carbide at high temperatures. And when I mention high temperatures, I really mean temperatures that are above 1500, typically 1500 degrees Celsius. And we know also very well how this proceeds. We'll first form a carbon layer, which is not graphene, but is a buffer layer, which has a certain number of bonding to the underneath substrate. And then as the buffer layer is released and a new buffer layer is formed, that buffer layer becomes a quasi-standing monolayer graphene on top of the buffer. And so this proceeds. So this works pretty well, and a lot is known these days about epitaxial graphene on silicon carbide wafers. How about, for example, growing graphene on pseudosubstrates? And what do I mean by pseudosubstrates? I mean a substrate made of silicon with an epitaxial layer of silicon carbide grown on top of the silicon wafer, which is something that we know how to do. There's quite a few capabilities out there regarding this heteroepitaxial growth of silicon carbide. Silicon carbide grows as a cubic polytype of silicon of the carbide, and the idea is that, well, can we transfer that beautiful approach of the silicon carbide wafers onto the pseudosubstrate? Well, it turns out that although in principle we can follow that type of principle, there's a couple of very important, how to say, bottlenecks here. First of all, there is a really large lattice mismatch between the silicon carbide and the silicon, as you probably know. It's about 20%. Because of that, and you can see here, these are two TMs of the cross sections of silicon carbide on the 100 phase and the 111 phase onto silicon. And you can see the amount of defects. This is inevitable because, unfortunately, due to that large lattice mismatch, this is the type of growth you can expect. Now, of course, if you want to use this layer as an epitaxial layer for graphene, because we're talking about epitaxial growth, the template is going to be, the fact that the template is very compromised by defects is going to transfer onto a very effective growth. Not even mentioning the fact that this thermal decomposition that works so well in the case of the silicon carbide wafers, in this case has another bottleneck, which is we cannot go at very high temperatures because we're working with silicon, so we need to be safely below 1400 degrees. So all of that together means that attempts at just translating that process have been always resulting in very defective and mostly not continuous graphene. So as you're familiar with the spectroscopy, Raman spectroscopy of graphene, you will recognize that the presence of not only the presence of really the ratio, the D band to the G band is really very unfavorable. So the D band is even higher than the G band, meaning that the layer is essentially fully really defective. So this doesn't work. Okay, we need to do something else. Is it worth looking into that? Well, actually, we thought yes, for various reasons. Well, first of all, because if you were able to do that, you would be able to do also some selective growth. And I'll show you in a minute what I mean by that. Second, equally important is that you will be able to actually take advantage of the combination of graphene and silicon carbide. And that combination can be particularly interesting for quite a few applications. I mentioned here, one is the MEMS. I will show you how interesting it is, that combination for photonics and integrated optics. Remember, graphene by itself is really, the only material that makes a device. Graphene will always have to be combined with a certain material to complete the device, and that combination is going to really be key. So yes, we think that this is worth pursuing, regardless of the challenges. And this is where our main contribution has come along, which has started. So this whole platform we've been developing, it started a decade ago, roughly. And it has taken that long, actually, to refine this approach, understand really all the challenges and the bottlenecks, and also define the properties such that we could know what are the areas, the most interesting, more promising areas of application. And we learned also quite a lot of things about graphene that I will share with you. So first of all, how did we go about it? We decided that we needed to use some catalysts. Okay, catalysts usually always help to lower the temperature, first of all. But in this case, it wasn't just a matter of temperature. It's a little bit more complex than that. We selected nickel. That wasn't anything new. People have looked into using nickel for catalyzing graphene growth. Now, what is the principle of the nickel? Nickel forms silicides. So nickel can combine with the silicon of the silicon carbide and release carbon while forming silicides at relatively lower temperature. However, nickel by itself doesn't necessarily give you the result you would hope to have. As you can see here, when we use nickel, we also tend to have a really high D band. So we thought, okay, we need to do something else. Why don't we combine nickel and copper? Why is that? It's because nickel, as I said, will control the release of the carbon from the substrate, but at the same time, copper will be extremely good to actually catalyze the graphitization of that released carbon. And that we know because graphene is often grown on copper foils, and that's one of the techniques that works the best to really obtain large grain sizes graphene. So basically, see this as a kind of hybridization of the thermal decomposition on one hand and the growth on metal foils on the other hand. Although the principle is a little bit different. So first of all, we work at 1100 degrees, and there's a specific reason for that. At 1100 degrees, or slightly above that, the nickel silicides are, well, the copper is in a liquid phase, and the silicides are also liquid. So what happens is that when you do epitaxial growth in a liquid phase, you can benefit from a favorable, larger diffusion lengths of the atoms that you're working with, and so you have much more. You can release a lot of the constraints that are given, for example, by your defective template. And this is basically what is happening here. You can see when we use just nickel, we are up here, and when we use the alloy, so the thin film of nickel and copper that are alloying together, we can get down to 0.2. So it means we still have a D-band. Of course, we can't do miracles. You've seen the template we're working with, but amazingly, we can reduce it substantially and really make a continuous film over very large areas. Now, the other aspect of this that I need to mention is that when you cool down, well, basically what happens when you cool down, we are talking about all of the metals being in the liquid phase, and then it will be floating at the top. And then what happens is that in the end, while you form the graphene just on top of the silicon carbide, all of the reacted and reacted metal will be on the top, and you will be able to remove them, which is really, really, really good, very, very easy to use. So that's the principle. And by the way, we do not use ultra high vacuum. We use medium vacuum conditions. So we have some oxygen in the back pressure of the system. And this is important characteristics because you will see these are some synchrotron measurements, and we'll just kind of profile the sample the really, really top of the depth of our system to look at, for example, this is for the carbon C1s. This is the carbon related to graphene. Silicon carbide, of course, is there. And then as top 2 nanometers, when you select a new photon energy, you probe a little bit deeper. And at that time, you start seeing that the silicon carbide takes over. So the layer is very thin, of course, and so on and so forth. Now, if you do that with the silicon peak, and you start observing that there is quite a lot of oxidation, particularly in the top. And this is actually what happens, particularly here from this SPS depth profile, and then Tofsins also confirms that, is that you have the graphene on the very top of the system. Then you have a few nanometers of kind of transition, is not to the really silicon carbide yet, but is a silicon oxycarbide that is just underneath. So basically, the oxygen is part of our process and forms this very thin silicon oxycarbide that is also a little bit amorphized and low density type of material. Soon after, you have the silicon carbide underneath, the cubic silicon carbide. So I just would like you to remember this, because this will determine some interesting characteristics that I will speak about later on during the presentation. All right, so I mentioned early on something about the selective growth. And this is really, really a great advantage that we have in this platform. Why is that? It's because when you grow the epitaxial graphene on a silicon carbide wafer, silicon carbide, of course, is monolithic, and you basically don't have any potential to make any site selectivity. And the silicon carbide is also quite hard, notoriously hard to micromachine. But if you can do this, as I explained before, onto a pseudo-substrate, what you can do is pre-pattern the silicon carbide on silicon, which we know how to do is through dry etching. So you do that at the wafer level. And once you have pre-patterned the silicon carbide, which remember is also our solid source for the graphitization, then we can just put down our catalyst as a blanket layers. And the blanket layer, we just cover the whole wafer with no additional lithography. We will bring everything in the furnace up at 1100, as explained before. And then what's going to happen is that the metal is going to react with the silicon carbide and form the graphene in the way I explained, and form the graphene only where you have the availability of the solid source. So only where you have the pre-patterned silicon carbide. And this is what I mean by site selective, because that you can easily extend to the wafer level. And so you will be forming the graphene all around the silicon carbide. Everywhere else where only the silicon is exposed, what's going to happen is that the catalyst will react with the silicon forming silicides, and those silicides will be removed, as I explained before. And then once you've done that, you will continue just, depending on what type of device you're making, you will continue with the processing flow that follows. So this is really something that would not be possible using silicon carbide wafers, and would really be very hard to obtain by transferring graphene. The reason is that we can easily, in this case, what's going to happen is by pre-patterning silicon carbide, and it doesn't have to be necessarily a planar system. It can be also very complicated 3D structures like nanopillars, nanoantennas, for example. And you don't have to worry about covering all of those silicon carbide nanostructures with the catalyst layers, because the catalyst layer, remember, will be in a liquid phase, and so it will naturally flow all around, covering the silicon carbide. So this is a principle, and this was our early demonstration at that time, just a simple demonstration of site selective growth, where we had bridges of silicon carbide coated by graphene suspended onto silicon. So where you see the black area is all silicon, and Raman confirms that. So here there's only silicon to be seen, and the lighter parts are actually made of silicon carbide coated by graphene. So that's the principle, and that can be scaled up to wafer level, of course. So this gives us a lot of versatility, and this was just basically for our own, understanding. Are we able to scale this down to really, really nanostructures and really disordered nanostructures? So we worked with with colleagues of ours who provided us VLS-grown nanowires of silicon carbide. This grows as cubic as well on a silicon substrate. And this is just to show you that the process is really versatile. So we deposited our catalyst as a blanket layer over this forest of nanowires. And initially, as you can see here, we just had LO and TO, so it's only just 3C silicon carbide. After the process, we just tweaked it a little bit because we have less carbon, so we need to be careful how much nickel we deposit down. We can find a system that is made of, again, silicon carbide, much less this time because we consume some of the carbon, and then coated with graphene. Of course, you will wonder, why is the D band so high? Well, consider that these nanowires are about 30 to 50 nanometer diameter in terms of this forest. So of course, the deep band is going to be small. It's going to be high just because of that, because of the size of the nanowires. And this proceeds exactly in the same way. So we will be left with a core of silicon carbide with a shell of graphene outside, and with a very thin intermediate shell of silicon oxycarbide. I'll talk more about that when we talk about optical properties. Now, last but not least, a lot of you, of course, many of you are really involved in the microelectronics processes and fabrication, and I'm sure that many of you have experienced firsthand what it means working with materials that have poor adhesion. Now, graphene is a little bit of a philosophical discussion here because, of course, graphene is a 2D material. as a 2D material, what the only force that holds the 2D material attached to its substrate is van der Waals forces, no bonding in a Z direction. And well, it turns out that the engineering range of adhesion, so in terms of joules per meter square that can be measured corresponding to van der Waals forces, is around 1 to 2 joules per meter square. So all of these numbers from literature that I present here are very well, more or less in agreement with van der Waals forces, and you might have more or less work that goes into the bending of the material, and that's why you have some differences here. But that's the ballpark. Now, I forgot to mention we have typically a point ID to over IG ratio of 0.2. Okay, it's not 0, it's 0.2. We have relatively small grain sizes, and back on the envelope calculation, that means that we have about grain sizes of around 100 nanometers. So 100 nanometers, of course, will sound really small, right, compared to some grain sizes that are of microns and bigger. But hold that thought, because it all depends on the application that you're aiming at. Here we're aiming at more applications. We're not aiming necessarily at high mobility. And you'll find that that doesn't affect the conductivity. Now, this is a side aspect, but what I really wanted to mention is that the adhesion that we measured on our system of the graphene to the silicon carbide is about 3 times as high. So basically what is happening here is that around the boundaries of our grains, we do have some bonding with the underneath substrate. And of course, that happens because we have relatively small grain sizes. Now, this is very important, though, because sometimes for fabrication and for integration, particularly and for reliability, you have to find a sweet spot. You can't necessarily work with just van der Waals forces, because at some stage, unfortunately, during the fabrication step where you will have hundreds of mechanical thermal loads put into a stack while you're fabricating your device, the chances that this will fail are extremely high. And I can tell you from personal experience when I was working with locates, where porous locates were about that type of adhesion energy, and they wouldn't withstand a full fabrication procedure, even less bonding and packaging. So this is interesting because 6 joules per meter square, that's something we can work with. Okay, but now let's understand what we can do with this material. As I said already, we're not targeting high mobility because that wouldn't be really very helpful. But what are the areas that we can look into? So let's come back to that later. So first of all, we need to understand something about transport. So let me just go. This is really the one of the main points that I wanted to make. So we studied extensively the transport properties of this graphene on a pseudosubstrate, and we've done it at a large scale, just because we are really interested in scaling that up to full scales, full wafer, sorry. So our basically test vehicle, our typical test vehicle would be always this 1x1 coupons of material in a van der Waals configuration, where we study the whole effect, both at room temperature and down to liquid nitrogen or helium, depending on what we're doing. So we accumulated quite a lot of data about that. And here a snapshot of this. So as you know, when graphene, as I said, we're not talking about suspended graphene in vacuum, we are talking about supported graphene. And it is very well known that for supported graphene, this is a typical power relationship that we expect between mobility of the material of the carrier in the material and the sheet carrier density in the graphene. So of course they don't change independently. They're linked, and particularly they're linked by this power relation. So on a log scale is almost a straight line. And if you are on a for the same straight line, you would have to expect the same type of sheet resistance in this case. And actually, this is what happens. And we took data from literature. These were actually all data published by a collaborator of ours. And this was done on the epitaxial graphene on the silicon phase of hexagonal silicon carbide. So all of these triangles of different colors are all coming from that, and they extend up to here. So these are basically the distributions of the transport properties for this epitaxial graphene on silicon carbide wafers. Now we superimposed our own data. And remember that we can do this exercise both on the 100 and on the 111 phases of the system. And actually, this is what comes out. It comes out that our numbers, without doing anything, they really fall exactly onto the same line, which is, well, initially it was surprising, but then after all, this is, if it is graphene, it has to fall onto the same line because they have to have that type of graphene resistance, right? And what really varies here is that we are skewed towards the high sheet carrier density area. And by consequence, we have lower mobility numbers, of course. And particularly, well, by the way, another important thing is that our carriers are always P-type, which is different from this situation. Usually they are N-type. We are P-type, and I'll explain you in a moment. And also, last but not least, the 100 always tends to have higher sheet carrier density than the 111. Now, before I explain why this difference, I wanted to again stress the fact that these literature values were coming out of graphene with really large grain sizes. We're talking about microns and higher. These data here are coming from smaller grain sizes, as I mentioned before. Same grain size approximately for both of them, but much smaller than these points here. So really what you find is that in terms of resistance, of sheet resistance, for example, for this epitaxial graphene, this does not matter. We have all the same ballpark sheet resistance. But what really matters is the different distribution of sheet carrier density and hence different mobility values. And basically, I will stress the fact that, and I will show you in a minute, that we are really interface dominated in terms of transport characteristics. And this is what explains this difference. Bear with me in a second. So we worked with on DFT with collaborators, and we modeled our different phases, so the 100 and the 111, and our growth of epitaxial graphene on top of those. And remember, we have some oxidation, okay? So we had to take that into account. So we have a layer of oxidation here on the 100 and a layer of oxidation here on the 111. Now, the main, what happens, and this is very well known, graphene is basically doped by charge transfer. And exactly that's why you could never consider graphene by itself in a vacuum. When it's surrounded by other materials, there would be a certain amount of charge transfer. And particularly when you have this type of oxidation, if the charge transfer onto the graphene because of the proximity of the layer will be P-type, okay? And this is exactly what we see. So for 100, we have a maximum amount of P-type charge transfer, high sheet carrier density, which comes directly from the oxidation of the top of the silicon carbide. Now, the 111, what happens there? The 111, as we know, because that corresponds also to the 0001 phase of the hexagonal silicon carbide, we can form a buffer layer. We can't do that here on the 100, but we can do that on the 111 surface. So the first layer to be grown is actually a buffer layer, which is not a graphene. It's just a carbon layer with the same morphological aspect, but it has bonding, so it's not active. And what happens then is that, but the buffer layer basically can at least partially screen It's like a screen that is in between the graphene and this oxidation. And basically what happens here is that because of that screening, there is substantially less charge transfer onto the graphene on top. So this makes perfect sense. So we are really interface dominated. And it's really, really important to understand, because in this regime, it wouldn't really matter too much how much bigger the grain size are necessarily as we are. But what is really important is the control of the interfaces. And this is absolutely essential for the integration of graphene, for understanding the integration of graphene and for controlling the integration of graphene. And of course, the full integrated graphene would have not only a bottom interface, but it will have also a top interface. So both of them have to be really, really finely engineered. All right, so now that I explained to you mechanical, electrical and electronic properties and physical properties of this graphene and our learnings about the grain size versus the interface and all of these basic aspects, I would like to share with you a little bit more about the applications. And so after this many years of refinement of both the graphene growth as well as the control of the silicon carbide to silicon interface, which is really, I won't be able to talk about that now, but it's really key. We have been moving towards integrated applications. One of that is optical. So why is that important? Optical integration, so integrated optics, is clearly lagging quite a way behind integrated electronics. But there's a lot of aspects that are really important for us to learn, for electronics, and try to apply that as much as possible to optics, striving towards the ultimate miniaturization. Of course, if you have to use the classical lenses, there will be no way we are able to miniaturize that. But what happens is that we are now aware of this very appealing theory of the meta surfaces and metamaterials that are really, they give you an incredible leverage to optimize and engineer materials that are not available in nature, just by nanostructuring and by tricking the light, if you want. So by using nanostructuring or even microstructuring, which with pitches that are sensibly smaller than the wavelength of light, so that the light sees as a whole uniform layer. Before I start talking about this application, I would like to share just the fact that we are part in Australia of this Centre of Excellence for Transformative Meta-Optical Systems, or TMOS, recently launched. So we are 15 CIs all around Australia, all focusing on miniaturization of optics through metasurfaces, but different aspects of that. So the generation, manipulation, and detection. All right, so we specifically are currently working a lot on the detection aspect with this graphene silicon carbide system, and particularly in the mid-infrared. Why is the mid-infrared so interesting? And I'll show you in a minute. Really exciting that came at a really good time. It's so exciting. So there's two aspects. One aspect is, for example, you are able, by using MIR light, to probe at standoff distances chemistries. Chemistries, for example, there's quite a lot of fingerprints of molecules, a few are here, that actually respond in the mid-infrared. So methane, or it happens that methane and CO2 are two of the biggest responsible for climate change. So that's an interesting observation there. So that's one thing, the chemical information at standoff distances. Second part is imaging, detection for imaging. Of course, the thermal imaging happens at mid-infrared wavelengths. So that's already one example there. And also systems like LiDAR, so light-based radar, are very interesting. They're moving towards already near infrared. Eventually, potentially, would be towards moving towards mid infrared. The reason is that you want to be able to pump enough power in the system in order to get a good image back from the photons that are scattered back. But you can't do that in the visible, because if you do that in the visible, it's not eye safe. You have a very low threshold in order to stay eye safe. Infrared can help a lot of that. So basically, these are the two main areas in terms of detection: chemical sensing and imaging. Very nice example. So I think most of you have seen this, the beautiful images coming back from the James Webb Telescope. And the James Webb Telescope has actually a combination of different detectors, imaging detectors. The main two are actually in the infrared. One is the NIR and one is MIR. You can see that from the IR, you can get an idea of the chemistry in some faraway galaxies, for example, as you can see here. And the imaging, you can see things that you wouldn't be able to see in the visible information that is really important. And not only, but between the NIR and MIR, you get different types of information that you can distinguish for. And this was a beautiful image where you could see, for example, the NIR, just one single star in the middle, and MIR, two stars that could be detected. So MIR is really very exciting in terms of, and also from an electronic perspective, you start approaching more and more the terahertz spectrum, which is something that probably I won't be able to talk to you today. Now, so MIR, hopefully I have convinced you of how interesting that is. Now, why am I talking so much about MIR? Because it turns out that our system of graphene and silicon carbide is particularly responsive in that area, in that region. The idea, indeed, is to actually combine the surface plasmon supported by the graphene with the surface phonon supported by the silicon carbide. The silicon carbide has a surface phononic response in the rest-Rayleigh band, so between the TO and LO. And actually, it turns out, and our collaborator Josh Caldwell from Vanderbilt has done a lot of work on that, on the silicon carbide by itself. Silicon carbide can be considered a really low-loss material compared to typical plasmonics material like metals that have lots of losses. With the silicon carbide, you can really get a very, very low loss and high Q response due to this, to the surface phonon. Drawback is that the window where the silicon carbide, you can elicit the response of the surface phonon in the silicon carbide is limited to rest-Rayleigh. And the rest-Rayleigh is quite a narrow band in between, as I said, the TO and the LO of the silicon carbide. So yes, it's low loss, but it's also very narrow band, and there's not much you can do about it. However, when you combine that with graphene, the plasmon and the phone and the surface phonon can hybridize. And this is really the exciting part. So if you look at the dispersion curve, this is just back of the envelope calculation just done on a simple flat surface. So then of course you have to consider for real cases the actual nanostructures, but just to explain. So for example, you have a free photon in the space that you want to capture. And so how you do that is by basically intersecting that with your response of your system. But if you're using only the silicon carbide, you have, as I said, a very, very narrow band. You can do this. Now, if you combine that silicon carbide with the graphene, at that point, something really interesting happens. Because of that hybridization, you are able, one, to enlarge that responsivity window from the rest-Rayleigh to quite a sensibly larger window. Second, very interesting one is that you are able also to tune it around depending on the charge concentration on the graphene. And so low charge concentration would be this distribution, and high charge concentration would be tuned to the other end of the spectrum. So this is something that not only can give you a low loss system that has a larger responsivity window, but is also tunable. And this is the holy grail in a way. So this is what we're pursuing, okay? And we're doing that by fabricating these nanostructures made of silicon carbide coated by graphene. And I give you a few examples. So we're looking into nanowires, we're looking theoretically into nanoparticles, and we're doing microgratings. Now, the nanowires you saw before, we can do also with just forests of nanowires. And we've been able to show that, for example, if you had a nanowire with just the silicon carbide itself, you would have this type of response where you have the TO that is always there, and then you have this surface phonon. So we're talking about near field here, by the way. You have the surface phonon response, which is within the restaurant. Once you combine that with graphene, forget about the TO, this is always there, doesn't really matter. But what happens is that this mode is basically split in two. And you have what we call mode 1 and mode 2 that actually appear outside of the restaurant band. These are hybridized mode. If you see the graphene mode, it will look very different. It will be up here. So these are real, purely hybridized mode from the phonon, the surface phonon of the silicon carbide and the plasmon of the graphene. And then very interestingly, because remember that we have that thin silicon oxycarbide in between the core of the nanowire and the shell of graphene. And the silicon oxycarbide is actually a low refractive index type of material. And we have also observed that acts as a coupling medium. So you can see that from this field map of one, I believe is M1 that I'm showing here. And the field is highly concentrated in those few nanometers of low refractive index material in between the external shell and the core of silicon carbide. So not only you improve your responsivity outside the restaurant band, you increase the amount of absorbance in the mid-infrared, and you're able to actually focus the field into a very, very focused ring around following the low refractive index system. This has a lot of interesting implications, for example, for sensing, for chemical sensing including. Very similarly, we've done the same exercise of looking at the nanoparticles and similar stories. Now, an interesting thing about nanoparticles is that these nanoparticles would respond again in the mid-infrared and with size that are relatively small. Whereas if you had to use nanoparticles of typical plasmonic materials, so metals and such, in the infrared, their size would have to be much bigger. And we're talking about microns. Now, when you start having particles or microns that have to be ingested or inserted somehow in the body, they cannot be easily metabolized. So it has really a quite interesting implication from point of view of medical and biological application. Now, one thing that we're really looking into, so is the enhanced absorbance in the infrared, of course, but we're looking also into all sorts of different filters that we can make by designing top diameter surfaces. And this is just an example of angular dependency that we are studying by using gratings of silicon carbide and graphene. And one of the ideas is indeed, that's a work in progress, is that we're building phase imaging based on this type of gratings. Now, I just would like to remind that, as I explained before, one of the appealing sides of this technique is that we have almost infinite capabilities in terms of the fabrication wafer scale, meaning that we can do waveguides, we can do pillars, antennas of different types and different approaches, we can also etch into silicon. Sometimes that is also something that we want to do. So basically, what we have built a very solid physical model with COMSOL, HFSS, and different other modeling capabilities to represent the system, and we are continuously improving so that we are able to potentially make this predictive and design top down what type of metasurface we can design. Okay, and just remember that because we are working in the medium infrared, these structures don't necessarily have to be that small. They can be still in the micro range. All we need is that they're smaller than the wavelength that we're using. So yes, these are some examples of, as I said, imaging is one. So building matrices of filters for imaging is something that we are doing with using this system, as well as we're looking also at biological and chemical sensing in the medium infrared by using CIRA. So CIRA, for those of you who never heard this, is surface enhanced infrared absorption. So you're really basically playing with the enhancement or local enhancement of the field, such that you can sense with much more intensity the single molecules. So you're enhancing that response. So without further ado, I can't enter more into the details about just because of time. So this is a big area for us, the medium infrared applications and the metasurfaces. Another area that we have been working quite a lot into, and this is very important for system integration and miniaturization, is in situ energy storage. Now, depending on the time, I probably won't, I think I need to actually probably even jump this one because I wanted to share with you. So sorry if I will be going very, very quickly on that. So basically, I will not talk about this and go directly to the main area that I wanted to mention to you, which is an area of application that is totally different from what I discussed before. Here we're talking about sensing with graphene on silicon, carbon on silicon, the same pseudosubstrate. And I will show you also a very specific application that we are actually doing right now, which is brain-machine interfaces. This work is being done in collaboration with my colleague, Situ Lin here, distinguished professor and expert of brain algorithms here at UTS and in his whole team, as well as the robotics arm division of the Australian Army that is working with us to develop these interfaces. So we're talking about electroencephalography here. We are staying away from implanted at the moment, just because it's not our area. It would be a much more complex area to do. There's a lot of groups working in that field. We just want to work with something that can be easily used outside of a clinical setting. EEG has been already used for a long time for various, for diagnostics in all of these areas here. I won't read them all of them, but you probably already know that. And more recently, this is the EEG has been applied also to brain-machine interfaces, and I'll show you in a moment what that means. Very quickly, we are electrical machines, if you reflected ever on this, but we are electrical machines powered by neurons. Neurons have ionic currents going through and transmitted to the next neuron through synapses and such. And so these all impulses go by basically the action potential. If the soma of a certain neuron receives enough signal to make it go above the threshold, a depolarization will be initiated and transferred through the action down to the synapses, and then that will repeat again. The synapses will transmit to the next neuron if the threshold is from the different inputs will be passed, and so on. So basically, as a whole, the neurons in our brain phi over certain pattern. And you can, with the EEG, you can detect the summation of the action potential. So what we call the postsynaptic summation. So how many neurons we're detecting? Tens of thousands to a million, okay? Because we are out here, we are relatively far from the cortex. So our spatial resolution is not particularly good. And so we're really looking at big ensembles. And these are the different type of brain waves of patterns and the frequencies we're looking at. So it's all very low frequency, as you can see, because as I said, we're talking about ionic currents. Now, one thing you need to be aware of is that because we are working here on the scalp, not here on the cortex, like, for example, Elon Musk would do with Neuralink, there's quite a lot of detonation just because of the presence of the skull and the scalp. All right, so you can do a number of things here. You, of course, need to know the anatomy of the brain and what the different areas and lobes are doing. And depending on whether you're looking at, cognitive functions, then you would look at the frontal lobe. If you're looking at the visual lobe, it would be the back, the occipital one, which is the one that we're using. And so basically, depending on what you're looking for and what type of application you're looking at, you will have to position the EEG sensor in the correct place. Now, I will have to really, I have just a few minutes to go, and that's too bad because I could talk for very long about this. But one of the main challenges of EEG is that in clinical settings, in the clinic, in the lab, it works very well because you're using wet gel based sensors that are really they make a really good contact with the skin, purely resistive. But unfortunately, that's the golden standard, but you cannot take it outside because you cannot imagine having people going around with swimming caps like that, where you continuously have to replenish the gel. So basically, people have been working towards developing very performant dry sensors for a while, okay? And an additional challenge is the presence of the hair that you can understand very well. So when you go to dry sensing, there's always a capacitance component on top of the resistance. So you will always have a higher impedance there. There's no way around that. And that's been always a challenge. So we decided to use graphene. Both graphene actually and silicon carbide are very biocompatible. Graphene is very conductive. So we thought, okay, why don't we try and see if we can develop something that can be useful for EEG sensing? And actually, we came up with something really simple. Okay, this is just a square of that pseudosubstrate with the graphene grown on top. The graphene is the part that goes on the skin, makes contact with the skin, and so that would be the part in contact with the skin. And then the rear, very interestingly, we know how to make this. Should be in principle, the silicon carbide to silicon would be a diode, a rectifying junction. But we know that is a very lousy rectified junction, and particularly if we use a highly doped silicon, that junction is completely leaky, meaning it really just draws the current through. So we can make a very, very simple sensor that immediately transfer the signal collected on the front end of the sensor through the silicon to the other end. And so all we need to do is engineer this backside, connect it to the socket of the helmet, and go from there. We could see that. So we did. I won't be going through all of this because I won't have time enough. But there's a couple of things I wanted to share with you. Actually, this system performs really well, and it performs definitely better than the most commercial tri sensors that are available. But also, there's a very interesting thing is that over just a few first minutes that you have the sensor in contact with the skin, we have a substantial reduction in impedance, contact impedance with the skin. Now, remember, we're trying to extract microvolt features out of those brain signals on the scalp. So low impedance is absolutely a must. So this is very interesting. This starts to be really, really competitive. And on top of that, a part that often is not there in the commercial samples is that these sensors turn out to be extremely resilient in highly saline solutions. Of course, with sweat, and the sensor will be exposed to sweat. If it's metal, very often it will start corroding. If it's graphene composite, probably will start delaminating at some stage. This does not happen in this case, because I remember that we have quite a significant adhesion of that graphene to the substrate. And so even after soaking these sensors for a long time in highly saline solutions, for example, the whole lockdown, we done some experiments of immersion, and the system is actually even more conductive. There is no failure, mechanical failure or delamination, and it's really resilient on the long term, which is something that our customer, in this our client, the Army, is extremely concerned about. They want not only the performance but also reliability. Very, very quickly, that decrease of impedance that you saw is basically because we're building layers of water around the layers of graphene. And that, interestingly enough, happens particularly well because we have these relatively small grain sizes. Indeed, we start from a hydrophobicity of, you see, contact angle with water is about 70, and we go down just by content on the skin, we go down to 34 degrees. So there is a substantial difference. And thanks to that, we can lower substantially the contact impedance, which is what we want. If we use a larger grain size graphene, like this one, in this case, your starting point is very similar. But then what happens is that we can't go down anymore in terms of contact impedance. This is because, and we've done a lot of studies on that, so I just say that very quickly. We're basically functionalizing with water-containing species, decorating the grain sizes, and then by that we are increasing, that's chemisorbed, but then we are increasing the physisorbed. We're basically forming a very thin boundary layer of water, and that is really important because that now enables you to find a sweet spot in between the really wet sensor and the dry sensor. Here we are, well, semi-dry sensor has slightly different type of approaches, but basically you understand that we are obtaining like a sweet spot in between that situation. This is to show you very quickly the fact that the sensors, once used on frontal lobe here, they give the EG sensors give a level of a quality of signal that is definitely superior to what we can see with the commercial sensors. And you can see, for example, the foam here give very little detail. You can see the difference between this signal here and there. You don't have to understand what this all means, but you can just remember that what we need is a high level of detail in terms of fidelity, in terms of detecting the biopotentials, so the AI can do its job as well as possible in terms of decoding the signal from the brain. Now, my last slide, I won't be able to explain to you the whole theory about how you do the brain interfaces and the brain-machine interface works. It works by paradigm, but actually our colleague from the Army here should be able to explain to you because he has used it. He has been working with us, and he should be able to explain to you how this works. Hopefully you can hear.
So the technology that we demonstrated today is called a brain robotic interface, and it's a way of a soldier operator being able to command an autonomous system and use their brain signals. So rather than voice or a command console or any other form of command, we can use an interface via a headset to allow them to move an autonomous system. And today we've used the Ghost robots because Recon has had experience with experimentation with this kind of autonomous system. Army absolutely plays a part in the development of this technology beyond the funding, and we have a range of use cases that we're looking to work with a range of stakeholders to ascertain the best way to test this technology and to help de-risk future acquisitions, particularly in the autonomous space.
The control I can exert over the robot is I can tell it to go to a number of, in this case, 6 predetermined locations. You don't have to think anything specific to make the robot operate, but you do need to focus on that flicker. So it's more of a visual concentration rather than having to clear your mind and have mindfulness.
Okay, so basically, this is the system that Damien is using. HoloLens, where the stimulus is given, and he chooses the option. The option is picked up on the occipital lobe, transferred to the decoding platform, where the AI will help identifying, classifying the type of response, and then decoding that into a command that is wirelessly transmitted to the platform, the electronic platform, robotic platform that we're using. In this case, is a Ghost robotic dog for the military, in order to be able to hands-free control the dog in cases of dangerous operation where they really need someone going ahead of them to scope out for potential dangers. So yeah, I won't be able to tell you more about this because of time. So I would really just like, at this point in time, we're very excited about this application, because finally we see graphene out in the field, and out in the field, really operational field with the Army. It's been really a fantastic collaboration, and we're learning every day more about how the system worked, and how, and we get a feedback about how we can improve the sensors. So if I can give you a couple of takeaways. So graphene is an incredible material because it can do so many different things. The important thing is to understand graphene in the context. So graphene, when it's integrated, how it behaves together with the other materials. So it's not only about knowing graphene itself, but knowing the interface of graphene, knowing the other materials that surround graphene, and targeting that to the application, and knowing also what application not to look into. So this is really, really important. For anything that is the sensing, for example, the electrochemical applications, I hope I showed you that actually in that case, having large grain sizes is not necessarily a good thing, because for the grain sizes that I showed you here, we have the same type of conductivity, but we need some type of chemical reaction in order for us to benefit from those type of application. And so last but not least, this combination of graphene and silicon carbide on silicon is very appealing because of the easiness of fabrication, and also the fact that you can basically use the properties of both these really good materials, because silicon carbide is also a wonderful material and can complement silicon technologies. Let me just finish by inviting you to Spring MRS next year, where we'll be discussing about how to accelerate miniaturized technologies for future electronics, from front end to back end to packaging to all of different types of integrated applications. So I will stop here because I want to leave at least a few minutes for questions. And thank you a lot for your attention and your patience during the talk. So thanks so much for that. Happy to answer questions. Thank you.
Thank you, Francesca, for this very nice presentation. So the presentation is open for questions. If somebody has one, please move to the front of the room. So I'll start with a small question. Francesca, can you say something about the electrical behavior of graphene under different temperatures, high temperature, low temperature, or so?
Yes, actually, I would have a slide. I didn't put it in this presentation. We looked both at low temperature, and we looked down at liquid nitrogen. We do that regularly, and sometimes with collaborators we do high down to helium, and then we looked up to, I think, 200, 300 degrees. That's the maximum temperature that we can do in our lab. Graphene is very flat, so the dependence on temperature of graphene, and this is what is expected, is really very, very mild versus temperature. But of course, you have to make sure that you're looking just at graphene and not at graphene with something else, and then that something else can give you some other underlying behavior. But graphene by itself has a very, very pretty flat behavior over temperature, and that's one of the characteristics of graphene, actually.
Oh, good. Oh, somebody, if you want, you can put your question in the chat, or you can move to this orange icon in the front of the room. So, Francesca, your presentation seems to be very clear, so nobody has any doubt. So I'd like to thank you very much for your nice presentation late at night in Australia. Oh, you are invited to join the conference any day that you want. And thank you very much. And we'll keep in touch.
Thanks so much, Michelle. Thanks, everyone. Bye-bye.
So now we have a 20-minute break, and at 10:40, we are starting with the second presentation in this mini-colloquium. So let's go to the break.
Oi? Hello.
Hello, Deji.
Hello. Sorry for the delay.
No problem. So let's move to the second distinguished lecturer presentation of our mini-colloquium, that it's the SBMicro 2022 Tutorials Day. So the second tutorial will be given by Dr. Deji Akinwande. Is that right?
Yes.
And it's about new applications of 2D materials from wearable health to memory devices and 5G switches. So just a brief introduction of Dr. Akinwande. He's a full professor at the University of Texas at Austin and a fellow of the IEEE and IEPS. He received the PhD degree from Stanford University in 2009. And his research focuses on 2D materials and nanoelectronics and technology, pioneering device innovations from lab towards applications. Professor Akinwande has been honored with several awards, so you can find it in the bio in the conference website. And his research achievements have been also featured by several media outlets such as Nature News, Time, Forbes magazine, BBC, and several others. And he serves as an editor for the IEEE Electron Device Letters and Nature. And please, Dr. Akinwande, the stage is yours. Feel free to share your screen. And yes, please put your presentation in presentation mode in PowerPoint or Acrobat, and then share the window of the presentation mode.
Yes. So let's see. Can you see this?
Yes, we can see it.
Oh, okay. Very good. Very good. So thank you very much. I'm very delighted to be present to talk at this conference. I hope one day we'll be able to also talk in person and discuss ideas. Today, I'll briefly, I guess, talk about some of our work on wearable and mobile health. And then, depending on the time, I can also talk about some of our work on the memristos and computing technologies. So I think, I don't know what the format is, but in person, I usually encourage questions anytime. But I suppose in the this virtual platform, I'll probably take questions at the end. And for the sake of the bandwidth, I may cut off the video just so the bandwidth is preserved during the course of this presentation. Okay, very well. So the research that we conduct in my lab is mostly focused on trying to exploit nanomaterials. In particular, we work on two-dimensional materials, and our interest is really to take new scientific discoveries or unique properties of these materials and study them, understand them, ultimately take them towards commercial technology and applications. So we like to say lab discovery to technological applications. In order to do this, we do very interdisciplinary research in nanomaterials and material science to understand this sort of materials. Then we make electronic devices, sensor devices, optical devices, memory devices. And then from time to time, we also find opportunities to make technological applications. So the focus of this particular set of slides on wearable health is an example of technological applications of these materials that we have studied in the laboratory. So let me use this opportunity to introduce this class of materials. I know there are several in the audience that are familiar with this two-dimensional materials, but then there may be others unfamiliar with this. So this two-dimensional materials, the easiest way to think of them is as a stack of paper. So you see on the slide, there's a stack of paper, and then you can peel one sheet of paper from the stack. So two-dimensional materials are essentially the atomic equivalent of a stack of paper. So the best known example is the graphite system. So graphite is more or less a stack of sheets of carbon atoms. And then you can peel one sheet of carbon atoms from this stack. And so when you peel one sheet, that one layer is what is known as graphene. The stack is what is known as graphite. And so within a single sheet, the atoms are strongly bonded, so covalently bonded, so they're very outstanding strength. In fact, graphene is the strongest known material because of the carbon bonding structure. But out of the plane in the Z direction, they're very weakly bonded. So it's exactly like the stack of paper. Also, the stack of paper has virtually no bonding in the Z plane. That's why it's easy to peel off one sheet of paper from the stack. So this anisotropic bonding, strong bonding in the XY plane, weak bonding in the Z direction, or so-called van der Waals bonding in the Z direction, is what defines this two-dimensional layered materials. So the graphite, as I mentioned, is the best known example. The physics, some of the unique physics in this material, such as quantum Hall effect, more recently magic angle superconductivity. Some of this physics has led to the Nobel Prize in 2010. Now, depending on who you talk to and what criteria you define, there could be thousands of these layered materials. And within this class of materials, you have basically every function that you might desire in a material system. So let me give you some commodity usage of these two-dimensional materials, because these materials are not new. They have been known for a long time, even though more recently some of their electronic and scientific properties are new. The materials themselves are very old. So graphite is a mineral. You can dig it from the ground. There are many deposits all over the world. The most popular application that you may be familiar with is in pencil. So the black stuff that you see in the pencil is graphite. It's in fact, because it has weak bonding out of the plane, that's why it can function as a pencil. So when you write on a piece of paper, flakes of this material then transfer to the piece of paper to form the pattern that you're creating. You cannot do this, for example, with a silicon pencil, because silicon has strong bonding in all directions. So if you make a pencil out of silicon and you write on a piece of paper, it will just cut the paper. It will not transfer any silicon material onto the paper. So graphite, that's example. Another usage of this is it's in lithium-ion battery systems as part of the electrode. So that's a more modern and recent application. Another popular two-dimensional material is hexagonal boron nitride. And one of the most common usage is in cosmetics. So this is used especially in eye makeup. These two-dimensional materials, because of this anisotropic bonding, are known as solid lubricants. They lubricate. So in the case of the cosmetic application, HBN can be combined with other materials. And then when the person applies it to their eye makeup, it absorbs moisture. So it keeps the face looking very brilliant. Even if the person might be sweating under illumination, the HBN absorbs all of this moisture, keeps the face dry and bright. So it's been known for a long time. In fact, back to the Egyptian dynasty in the ancient times, HBN materials, in fact, also carbon materials, were very popular for makeup applications for these reasons. MOS2 is also a popular 2D material. It's used as a solid lubricant in, for example, bicycles, motor vehicles, and so on, guns and stuff like this. So those are the commodity everyday usage that you may not be aware of. Nowadays, our interest is to define or pioneer new technological applications. So as I mentioned, within these two-dimensional materials, you can find basically every function you might desire. There are semi-metallic 2D materials, the metallic 2D materials, superconducting 2D materials, insulating, topological insulating, semiconductants, and even within this class, you can find piezoelectric 2D materials, ferroelectric 2D materials, and so on and so forth. And to utilize these properties requires understanding the structure of the materials, that's the material science, synthesizing the materials, and then investigating the ultimate limits of performance. So we, and of course many others in the world conducting research in this topic, study these properties, synthesis, and structure very, very meticulously. So in this particular presentation, I'll be focusing on applications towards wearable and flexible. On this image, I've shown several examples of what that could look like in terms of flexible wearable technology. And then if there's time, I may talk about other functions such as in memory store or memory technology. So let me give you some examples of some of these new technological applications of two-dimensional materials. I'll focus here on the case of graphene because it's the most mature of the two-dimensional materials. So graphene, we pioneered the use of graphene for gas sensing applications about 5 years ago. And the idea is the property, the unique property of graphene or two-dimensional materials for sensing that makes them, let's say, outstanding compared to other materials is the so-called surface to volume ratio. So this is the defining metric. Every application, you could define a metric. So for sensors, one of the fundamental material properties is a surface to volume. So you want very high surface to volume. What does that really mean? That means you want very, very, very large surface and very, very, very little volume. So the two-dimensional materials, especially in a single monolayer or single sheet, they are basically close to zero volume because the volume is just the, let's say, the diameter of an atom, in this case, a carbon atom. At the same time, they have a very huge surface because they're only two-dimensional in dimension. So you can get very large surface to volume. When you have very large surface to volume, it means that all of the atoms in this material are exposed to the environment. So if all of the atoms are exposed to the environment, that means they can participate in interactions with the environment. So they can be very useful in sensing, and you could have extremely high sensitivity. This is in contrast to bulk sensors. So if you made a sensor, let's say, out of silicon, typically it's very difficult to get a single sheet of silicon because it's not a two-dimensional material. So you have to make a reasonably thick silicon to get the bulk properties of silicon. So let's say you make 100 nanometer thin silicon. That means there's probably 100 nanometer there's probably 300 layers of silicon present. So, but when you expose it to the environment, only the top layer, the surface atoms, are going to participate effectively with the environment. So that means the remaining 299 layers that form the volume of the material are not effectively participating. So it's not very efficient. So in the case of the two-dimensional materials, all of the atoms participate if it's a monolayer. So this is the basic idea driving the research in sensor technology. So we developed this platform where the idea is you could have gas molecules of interest. It could be ammonia, some organic gases, and hydrocarbon gases. Any gas really that you want. And then when you expose a graphene, in this case, we design a silicon CMOS chip fabricated in TSMC foundry technology. And then we got the chip back and we placed graphene on the top surface of the silicon chip in a back end of the line process in our clean room facility here at the University of Texas. So when the gases are exposed to the graphene, because of the interactions with the carbon atoms of the graphene, they can dope the graphene with excess electrons or excess holes. So that means the resistance of the graphene will change, the electrical resistance. So you can measure this electrically. So then we need a readout system to process these changes in the resistance. So the silicon has electronics. In this case, we designed a ring oscillator. The ring oscillator converts the resistance change to a frequency change. And then this frequency change can be broadcasted by an antenna so that this is a wireless remote sensing platform. So you can imagine where you have toxic gases, you may just want to be able to read it out remotely, not physically, because it's a toxic gas environment. So here is shown pictures of the silicon CMOS chip, and then you can see here a graphene between two contact electrodes where we can monitor the change in resistance. So this was published 5 years ago. In the same year, my very esteemed colleagues in Barcelona, Frank Coppens and co-workers, they showed basically a similar platform. You have a silicon CMOS chip. They put graphene on the topmost layer, and then in their case, they also put quantum dots because this is designed to be a photodetector. So the quantum dot allows you to tune, to some extent, the light that you absorb, and then the graphene collects this electron on holes to convert it to electricity. And so this is now called the Graphene Camera, because by the use of graphene, you can have very, very high photodetector sensitivity over very, very broad bandwidth, because graphene absorbs all the way from the infrared to essentially the UV. So unlike commercial photodetectors that are mostly in let's say in the visible range or in the infrared, this is a very broad band. So you can use it for night vision, you can use it for regular camera applications and so on. And then the same year, very interesting work came. This is a Graphene Biosensor. This is from Kadia Bio. It's a company based in San Diego in California, where they have been pioneering a platform where, again, they're using the very high surface to volume ratio of graphene to sense biomolecules. And so this is, in fact, a commercial product. We have actually received this commercial product, and they sell this to strategic partners that you can engage with them on the internet. So we started actually working on graphene biosensors as well because of the COVID pandemic. We wanted to leverage our expertise in sensor technology, in nanomaterials, to try to address the pandemic challenge of diagnostic sensing. So one of the challenges with these nanomaterials is, even though they're very, very sensitive to basically everything, they're not intrinsically selective to anything. So basically, if you have graphene, it's going to be sensitive to everything in the environment. But what you really want in a sensor is something that is sensitive and only selective to the particular species of interest. So for the case of graphene sensors, the way to give it selectivity is to functionalize it. So we have the graphene channel here. And then because we want it to be sensitive to either, let's say, the COVID virus or the influenza virus or a specific variant of the virus, we have to functionalize the graphene. In this particular strategy, we're using the antibodies. Antibodies are natural molecules that interact only with the antigen, the viral molecule of interest. And so the bodies, our bodies naturally produce these antibodies when we're exposed, and these antibodies can then be synthesized in a laboratory. So for the case of the COVID-19, we functionalize the graphene with the COVID antibodies first. And so that means that if there's a COVID protein or COVID virus, when it interacts with the graphene, it's going to lock onto the antibodies. And then due to charge transfer between the COVID virus and the graphene, the resistance of the graphene will change, or the current in the graphene will change. And then you can monitor this externally through a reader. If you wanted to do influenza, flu, then all you have to do is just change the antibody to the influenza antibody. Let's say you want to do the latest variant of the COVID, then all you have to do is change the antibody of the initial COVID to the antibody of the latest version or latest mutation of the COVID. So very, very flexible platform. And in fact, what we decided to do is make multiple channels so we can do simultaneous detection of different variants and the flu virus all at once. So this is more or less a USB type implementation. That was our laboratory test kits, but now we have more professional test kits. This is now actually, we've spun this off as a startup company that is specializing in diagnostic sensing using graphene. And so this is some of our results. In this particular example, you see a dual diagnostic sensing. It can simultaneously detect whether it's COVID, flu, or none of this. So the black curve, for example, is when you expose it to a COVID sample. You see the current changes. The current is the y-axis, time is the x. You see there's a specific spike in response, but in the flu channel, there is no spike in response because it's a COVID sample. And then when you expose it to a flu sample, which is the black curve, the flu sample, which is the red curve, you see there's a specific spike in response in the flu channel of the sensor, but no spike in response in the COVID channel. So we can do multi-diagnostic sensing, very high limit of detection. And as I mentioned, this is already now a startup company technology. Okay, so I've given you some examples of using graphene nanomaterials for health technology applications. Now I'll move on to the focus of this presentation on wearable technology in particular. So before I go into some details, maybe I'll use this opportunity to just give you a background of how to think about the human body in terms of wearable electronics. I would argue that the easiest way to think of the human body is that the human body is more or less an electrical machine. It's electrical in nature. So what that means is twofold. So one is if you put wires on any two parts of the body, if you put any wires on the body, you can measure an electrical resistance because the human body is an electrical machine. So the human body is not a superconductor, it's not an insulator, it's full of ions flowing in the blood. So you can always measure any resistance of any point in the body. So this resistance is sometimes called the bioresistance or called the bioimpedance. Impedance is the inverse of resistance. Another thing is when you put cables on the human body, you can also measure signals generated within the human body. So these signals, again, is because the human body is not a superconductor, it's not an insulator, it has all these ions flowing, and these ions are changing. The concentration, the conductivity of this medium is changing. So you can always measure signals being generated from synaptic action, from neural action, from chemical reactions, from electromechanical contractions. And so these signals have now become very important in understanding the human body. And this has led to the field of electrophysiology. And electric means understanding of electrical signals generated in different parts of the human body. Then the third aspect of this idea that the human body is an electrical machine is that if you apply an external signal to the human body, you can stimulate the human body to have an electrical response. So this is then used for electrotherapy, for example. And it's also used in pacemakers. If the people that have cardiac or heartbeat problems, then you apply this stimulation, you could help resolve these issues. So in the case of electrophysiology, this has now been a technology for more than 100 years. The idea is to monitor these electrical signals that are generated within the body. So for example, you can put these cables on the head and you measure the signals generated in the brain area. And so these are called the EEG, or commercially, they're just called brain waves. If you put these cables around the chest area, you monitor signals generated due to cardiac activity. And so these are called ECG. And so all of these signals can be used to help understand the health and diagnose disease that may be in the brain, like, for example, seizure, epilepsy. These EEG signals are very important in understanding those conditions. If you have cardiac or heart problems, the ECG around the chest is a good indicator of the health of your heart. As you can see, even though these clinical technologies, I'm sure several of you have been subjected to this in clinical visits, you can tell that this is clearly not mobile technology. It's not wearable, right? You cannot wear these cables outside of the hospital because these cables connect you physically and tether you physically to a station. So they're not wearable, they're not mobile. So there was a revolution in thinking about 12 years ago by John Rogers, who was at the University of Illinois at that time. And he realized that actually you don't need these big cables to measure these signals, electrical signals from the body. All you need is conductive films. So if you could engineer conductive thin films and match them mechanically to the soft properties of skin, you should still be able to get all of these signals from the different parts of the body. So what John Rogers and his team, Dae-Young Kim and Nanshu Liu, did was make these thin films of metal and then placed it on different parts of the skin, made this serpentine structure so they were stretchable. And then they showed you could measure all the same signals that you could collect with traditional methods. So as you can see from these images, there are no cables dangling from these thin films. In fact, you could put a wireless, you could put an antenna around this and transmit all of these signals to an app on a phone or a tablet or external reader. So this led to the field of electronic tattoos. They're very light, portable, wearable, stretchable. So, now there's many research groups, many technologies trying to develop electronic tattoos for mobile and wearable health. So after the initial work in 2010, where the thin films of metal were at thicknesses of tens of microns, let's say 30, 40 microns, there was great interest to reduce the thickness of this metal thin films. And the reason is because the conformability issue. So when you have a metal thin film, metals are by definition rigid. So when you have a very thick film of metal on very soft skin, so the epidermis here is the skin, it doesn't fully conform perfectly to the corrugation or roughness of the skin. So everybody has rough skin. Even if even if your skin doesn't look rough in the mirror, when you put it in the microscope, you're guaranteed that your skin is rough. So even baby skin is rough. So it's not a very flat surface. So when you put these thin films of metal that are, quite thick, it doesn't conform perfectly. So this has several consequences. One of them is that there's going to be sliding. A brick of stone on rubber. The brick of stone, let's say, represents the thin film of metal. Rubber represents the skin. The brick of stone is going to be constantly moving because it cannot secure itself onto this soft platform. So this sliding is what is known as motion artifacts. The sliding of this film creates artificial signals that look like noise and can corrupt the real measurement that you need to record. So this motion artifact is very difficult to remove by signal processing and filtering techniques because it's quite random and it depends on person to person. It depends on time. The motion artifacts in the morning may be different from in the evening because the hydration or humidity of the skin may have changed. The temperature of the skin may have changed. So for these reasons, it's very difficult to get high signal to noise ratio. Another consequence is that the metal can delaminate from the skin because these air pockets create a weak connection to the skin. So after you wear this for a few hours, it could delaminate. So to make sure it lasts longer, you have to put a very thick tape around the electronic tattoo to secure it onto the skin. So what researchers realized is they could address this problem by making the metal thin film thinner and thinner. The thinner you make this metal thin film, the better it will conform to the skin and the less motion artifacts you're going to get and the longer and more reliable it's going to be. So this is exactly where I come into the picture. I started thinking about this and I realized that actually the thinnest conductor in the world is graphene. So maybe graphene could be electronic tattoo electrode. And so with the graphene, monolayer graphene with some support, it conforms perfectly to the skin, and we have shown this. There is no motion artifact at all, and it stays on the skin even without any adhesive tape. So it's very robust. It can last several days, and in fact, it can even last up to a week with reliable signal and to noise ratio. So this led us to invent this, what we call the graphene electronic tattoo. Ultra thin material means that it conforms perfectly to the skin. As I mentioned, it has no motion artifacts. Ultra light means that it's transparent. So in fact, we've enhanced this image so you can see it on the face of the model. But for most people, it's transparent. It's very difficult to see, and it's imperceptible, which means that you don't feel it. It's so light that when you put it on your skin, you don't even feel the weight of this sensor on you just don't feel it. So it has many advantages, and I'll show you some of the benefits of these advantages. So with the invention of electronic tattoos, this has opened up new technological applications. So the obvious one is, of course, mobile health monitoring. Then you have examples in human-machine interfaces, athletics. That's a very major area for wearable electronics, and then even more recently, fashion. So in my lab, we have a holistic view. We want to understand the bioelectrical signals within the body using this electronic tattoo technologies, mostly graphene and other two-dimensional materials placed on different parts of the body. And then oftentimes this signal that you get from the body needs to be processed, either to improve the signal to noise ratio or to convert the signals to something that is a medically relevant parameter. And I'll show an example in the case of blood pressure, for example. Oftentimes we need to add context to the data because, for example, let's say we're recording blood pressure. If the blood pressure is very high, that may be a cause for alarm. That may be an emergency. However, if the person has very high blood pressure when they're doing extreme exercise, let's say they're running or bicycling, actually then that context tells you that that is not an emergency. It's very normal that the blood pressure should be at a higher level during exercise. So context is very important in order to interpret data. And then when you get enough of this data, this can lead to the idea of a digital twin. Digital twin is an idea that is becoming more popular in medical technology. The main idea is to be able to collect enough data so that one can create a model of a human being. Let's say Julia, is a female person. It would be nice to get as much data, maybe from wearable electronics, that can create a picture or model of how Julia will respond to different environments. How Julia, if she's sick, can respond to different treatments. So by continuously monitoring the wearable data, all of the electrophysiological data, blood pressure, vital sign data, such a model can allow prediction so that personalized medicine can advance to the next level. So this, I think, is the future of medicine, is to use digital twin. Very similar to how before you build an aircraft, you have to model how the aircraft is going to perform. Before you build a car, you model how the car is going to perform, optimize the conditions so you get the necessary outcome. Okay, so making these electronic tattoos themselves, especially from graphene, is now a very straightforward process. I encourage you to read our Nature protocol paper by my postdoc, Dmitry Kirev. He has all the details and a lot of videos. We have undergraduate students making this in the lab. You can make dozens and dozens every day. It's now very straightforward. Typically, the graphene is placed on tattoo paper that you use for temporary tattoos, and then you just transfer the pattern. Whatever pattern you want, you transfer it to any part of the skin. And then the graphene, as I mentioned, is an extremely stretchable material. And so when the skin deforms, the graphene deforms without any damage. You can see the skin is wrinkled here. The graphene conforms perfectly to the wrinkles of the skin, and it doesn't delaminate. There is no adhesive securing it. It just stays on the skin due to the van der Waals interaction. So when you do this sort of new technologies for the first time, especially related to medical applications, you have to benchmark data with existing commercially approved medical technology. So ECG, I mentioned earlier, is a signal that you can record from the chest area related to cardiac health and activity. And here you see the graphene is the black data. The accepted medical standard, commercial standard, is the orange data. And you see very similar response between these two. Even though graphene is, let's say, 1 million times thinner than the commercial standard, which is a gel electrode, the graphene still provides a similar signal to noise ratio and signal fidelity. EMG is the electrical signal due to muscle activity. The graphene is orange in this case. Again, you see similar signal fidelity. You can also do physiological measurements like temperature. That means you can extract the temperature by measuring the resistance, temperature coefficient of resistance and resistance change of the material on the skin. And you see here that you can measure within the reasonable range the temperature change. And also the skin hydration means basically it's a measure of how hydrated the person is. Again, you can do that with the graphene just like you can do it with the commercial standard. So the skin hydration, for example, is very important for athletic applications of the electronic tattoos. Now, you can also do things that are very difficult or almost impossible to do with the commercial standard gel electrodes, and that's the EOG. EOG is electrical signals you read around the eyelids that relate to eye health, your eye activity. So when you look up, down, left, and right, your retina is moving. So that means there's electrical signals being generated. And then these electrical signals have certain profile that you can deduct the movement of the eye. So for example, if you have a blink, that shows up as a very sharp spike. If you look down, the electrical signal is negative. If you look up, the electrical signal is positive. And you can also differentiate when you look right and when you look left. So because the graphene tattoos are imperceptible and transparent, you can put them around the eyelids and it doesn't affect the beauty or aesthetic of the person wearing them. This is not possible to do with commercial electrodes, and it's definitely difficult to do with metal thin films because then it will affect the aesthetic of the person. So we actually took this to the next level to demonstrate a human machine control, which I hope you can see this video. This subject is wearing these graphene tattoos around the eyelids and using his eye movement to control the drone. So you can see his eyes are moving up, down, left, and right. The drone is respecting that command of his eye movement. So in this particular case, we have a wireless transponder at the back of the head of the subject that converts the electrical signal of the eye movement to commands to the drone wirelessly. So this may not be a very practical application because the eyes will get very tired after a while. But nonetheless, this is an example of using gesture, human gesture, to control machines. It could be eye, it could be muscle, it could be hand, it could even be speech. We can get all of these signals from these electronic tattoos and send them through after doing some basic signal processing to command an external object. This is another example. It's a little bit crude, but it shows that you can make everything wirelessly. So yeah, you may not be, it's very difficult to tell, but the graphene tattoos are actually the bottom of the chest area. It's almost transparent. And then what we have is we have a chip. The chip is in this package here. And then this signal from the graphene is transferred to the chip through these gold ribbons, these gold wires. And then the chip has power, it has a battery, and it has wireless capability, so it can send the connectivity, so it can send the signal to an app on an external device. So this is designed for athletic applications. So you can see the heart rate, Other relevant signals can be collected from the tattoo, like graphene tattoos, and transferred to some app on a tablet or a phone. So we continue to be interested to make this a more elegant integration. Anytime you work with the graphene tattoos and you have to put a chip, the main challenge is how do you integrate this in an elegant way that preserves the unique properties of graphene, but also gives you the data transfer capability for wireless application. Okay, now I'm going to move on to another measurement of human potential. So the ones I showed you earlier, those are the electrophysiological data, electrical signals that you can measure from the human body. And I showed also the physiological data, like temperature. Temperature is, of course, a vital sign. There are other vital signs that are also very important to measure. One of the most important is the blood pressure. And blood pressure, I'm sure many of you, if not all of you, have experienced this. Usually when you go to the hospital, it doesn't really matter which kind of hospital you go, which kind of medical attention you seek. If you go to your dentist, if you go to your eye doctor, if you go to your family doctor, if you go to any doctor, normally the first measurement they're going to take is your temperature and blood pressure. So blood pressure is a vital sign used to diagnose and, in fact, understand many diseases, including heart disease. And blood pressure is the leading cause of death in the world. More deaths originate from blood pressure disorder than any other disease, any other natural or unnatural catastrophe in the world. Blood pressure is the leading cause. Oftentimes it's called the silent killer because many people that have high blood pressure don't even know that they have high blood pressure, and suddenly they may suffer hypertension or stroke, and then this in many cases can be fatal. So it's a very silent killer, and it's all the more important that technology be developed to proactively monitor blood pressure so that everybody can be informed of their blood pressure, and if it's high, they can treat it before it becomes fatality. So what is blood pressure? Blood pressure is the force of blood pushing against the walls of the arteries. So the way to think about this, I know I told you earlier that you should think about the human body as an electrical machine. In the case of blood pressure, you can think of the heart as a mechanical machine. It's a pump. So just like any other pump, like a water pump, oil pump, it's going to have cycles in which it's pumping a lot and cycles in which it's pumping a little. So the cycles in which it's pumping a lot means that you have more blood flowing, and this blood is flowing through the arteries. So because the artery itself is not a rigid, it's not a rigid vessel, it's permeable. So when you have a lot of blood flowing through the arteries, they exert pressure on the walls of the artery, and then the artery expands. And then when the heart is pumping on the low cycle, that means there's less blood flowing in the arteries and the arteries contract. So altogether, this is a wave motion. So it translates directly to mechanical pressure on the arteries. So shown here is a complete one cycle wave, mechanical wave of blood pressure. So on the y-axis is the blood pressure. It's often measured in millimeters of mercury, and it ranges for normal people from around 80 to 120. So the minimum of this pressure wave is called the diastolic pressure. The maximum is called the systolic pressure. So oftentimes when you go to the hospital, or if you measure this by yourself, you just get these two numbers. You just get the maximum and minimum, systolic and diastolic. And how do you measure it? The technology to measure blood pressure, the sphygmomanometer, let's just say this is called the cuff. That was developed around 120 years ago. So it's an old technology, it's a mechanical technology. And what you do is you put this cuff around your arm, and then you apply reverse pressure. You pressurize the cuff until it cuts off blood flow in the arteries. And so when it cuts off blood flow, and then you do the opposite when it allows maximum blood flow, this allows you to extract the systolic and diastolic pressure from this reverse pressure application. So this is a clinical technology. I won't go into further, I'm not going to explain more details about how the principle of this cuff, but you can find it on Wikipedia. But it's very successful clinical technology. That's why it's used every time you go in the hospital. As you can see from this illustration, this is not really a mobile or wearable technology. It has several problems, several challenges. It's bulky, so it's not very mobile. You cannot do continuous reading. It's obtrusive because you have to make, manually, even if you automate the reverse pressure you apply to the cuff, that takes time. So it's a very slow device. So you cannot do continuous reading, beat to beat. You can only do a few readings per day. If you go to the hospital, they usually only do one reading or two at the most. So it doesn't really give a picture of your blood pressure or your whole body health, because it's just a snapshot that is very limited in time. And then some people suffer so-called white coat syndrome. So when some people go to the hospital, the environment already stresses them out. So imagine you're going to the dentist, you have to have a cavity or a root canal. That already creates stress. So this stress that one experiences in the hospital leads to artificially higher blood pressure. It doesn't mean that the person has high blood pressure, but it's very difficult for the medical professional to separate, is the person having this high blood pressure in the hospital today, is it because they're in the hospital, or is it because they have hypertension? So that's something that's very difficult to separate. So in some hospitals, they may say, oh, you may have hypertension, let's give you treatment for hypertension, but the person actually doesn't have hypertension. They're just having anxiety because they're in the hospital. In other cases, the person does have hypertension, but then the medical professionals may say, well, maybe your blood pressure is just high because you're in the hospital. Don't worry about it. When you get home, you'll probably be fine. So you have these two responses that the medical professionals may not know actually what the true situation is because of this white coat syndrome. So the only way to resolve it is if one could do continuous measurement over time. And then you could tell if the person has really high, truly high blood pressure, hypertensive, or they're just normal blood pressure. Another challenge is the cuff is not a very easy platform to use to do measurements. So there's significant variability. So there's some cuffs now that you can buy and you can measure them, use them on your own to get your own blood pressure recording. And if you go on the website and look at the reviews, you see that many people complain that their readings are not consistent. And that is because the cuff requires specialized skill in collecting this measurement. So if you're not sufficiently specialized, your reading could be very inaccurate. Even if you do a reading right after, back-to-back readings, both of them could have significant variations in the measurement because it requires quite a skilled expertise. So because of this, there's been interest to develop new methods of recording blood pressure that are more mobile, wearable, user-friendly, and so you can do continuous recording of blood pressure. One of the more mature developments is the optical measurement of blood pressure. This is widely known as PPG. This is not really a commercial technology yet. We wrote about this a few years ago. You can read our opinion piece in the journal cited below. The main idea is you can measure the concentration of oxygen in the arteries when blood is flowing. So the way you do that is you shine light, and then depending on the amount of oxygen, or you could say depending on the amount of blood in the arteries, the absorption of the light is going to be different. So when you have a lot of blood flowing, that means you have a lot of oxygen. So the light that you shine is going to be absorbed more. So when you measure the transmission of the light, you're going to see a fluctuation. This fluctuation has the same frequency as blood pressure, because when there's a lot of blood, that's the systolic, when it's at the maximum, you're going to get a lot more absorption of light than when you have less blood, when it's at the minimum. So that will be the diastolic. That means you have less absorption of light. So you can then either measure the reflection of this light or measure the absorption of this light, and you get these signals that resemble blood pressure. So this is so-called PPG. And then if you do some analysis, signal processing, machine learning analysis, you can convert this PPG signal to the arterial blood pressure. So this is actually a very promising technology. However, it has some challenges that has yet to be resolved. First of all, it doesn't work so well when if a subject has a very fat finger or fat hand. The fat tissue then absorbs a lot more of the light. So the accuracy and reliability of this method is not as good when there's a lot of fat present in the subject. So that is one issue. The other issue is it's also not as reliable and accurate for darker skinned people. So people that have more color in their skin, that also absorbs more light than people that have less color in their skin. So the reliability is also not very solid. So this remains challenges for this PPG modality that is the subject of more research today. So we decided to focus on an electrical method. So I mentioned earlier that you can think of the human body as an electrical machine, and you can apply signal to the human body and measure the resistance or impedance. So this is what we call the bioimpedance. So it's a very simple concept. As you know, and I've mentioned, the arteries carry the blood. This blood is carrying ions. Ions have a certain conductance or impedance. They are not superconducting, they're not insulating. They're like a cable, a wire cable, just like you have cables to your TV. So there's a certain impedance. And you can measure this impedance by doing a standard electrical measurement. In electrical engineering, this will be known as a 4-point probe or a Kelvin probe. So you inject current. This current is going to flow through the arteries, and then you have internal electrodes, all of them in this case made with graphene. And these are the sense electrodes. You sense the voltage. So then you can divide the voltage by the current, and then you get impedance. And because this is biological sample, in this case a human body, we call this the bioimpedance. So there's several papers already that have established the theory of bioimpedance. So the main hypothesis is that the bioimpedance should correlate with blood pressure, because when you have a lot of blood flowing, So when the heart is pumping and you're at the maximum blood flow, which is a systolic, that means you have a lot of ions present in the blood flow. So the impedance is going to be less. And then when the heart is pumping on the low cycle and you have less blood flow, that means you have less ions, and so the impedance is going to be on the maximum. So you have an inverse correlation. So shown here is blood pressure. You see in real time. And then at the same time, this is the bioimpedance collected at the same measurement time as the blood pressure. And you can see that there's a clear inverse correlation between the blood pressure and the arterial bioimpedance. And so you can say, well, can we quantitatively convert measurements of the bioimpedance to get blood pressure? So there are certain equations that tell you what the velocity of the wave is. This velocity is related to the elasticity of the arteries. And then if you could then get the elasticity of the artery, it's related directly to P. P here is the blood pressure. And this blood pressure is also related to the transit time. So if you can measure some of these parameters, you could get an idea of what the blood pressure is. But it turns out that there are a lot more variables involved. So there's no direct equation or set of equation that is sufficient enough at this moment that can accurately convert the measurement of bioimpedance to clinically accurate blood pressure. So let me just show you some more images of how this data is collected, how the graphene sensors are implemented. Right now, this is still, we've not developed the wireless version, so this is the wired version. So here are the graphene tattoos or electrodes, 1, 2, 3, 4, 5, 6. We place them directly on the arteries. There are 2 of them, one on the left and the other on the right side of the hand. And those are the radial arteries and the ulnar arteries. So this reddish color is just artificial, just to highlight where the arteries are. We use an experimental method to directly determine where the arteries are before we place the graphene tattoos. And then we have 4 channels of this bioimpedance. The minimum we need is 2 channels, but we did 4 channels just to get more accuracy. As I'll show you, we use machine learning methods so we can get more training and better accurate data. So in channel 1, we have the current injection channels, electrodes, which are the outermost graphene, and then the 2 innermost to the left of the upper side of the arm. That's the bioimpedance channel 1. So we measure the voltage there, and then we have bioimpedance channel 2, which is to the right of the artery, and then because we can simultaneously measure bioimpedance channel 1 and channel 2, we can also determine how long it takes for the pulse to travel through the arteries, because we're doing simultaneous measurement. So we can measure the delay in channel 2 with respect to channel 1 to get the pulse transit. So you need this sort of data ultimately to do the conversion of bioimpedance measurement to blood pressure. Okay, so because it's a complex relationship, we actually use machine learning regression model, statistical model, where, again, the basic idea is the heart is a mechanical pump. And so this pump leads to a pulse wave, a blood pressure wave. The pressure wave leads to volume change. There's a blood volume that results in blood pressure, because as you get more volume and less volume, it puts pressure on the walls of the arteries. Because the arteries are getting wider and narrow, the impedance is changing. So a wider artery just means like you have a bigger cable, so it has less impedance. A narrow artery means you have a skinnier cable, so it has more impedance. So that leads to bioimpedance change. Ultimately, you can measure this as a voltage change when you apply current. So we then have to do a machine learning regression model. We take a lot of parameters of the experimental measurements, like time parameters, the transit time features from the bioimpedance measurement. I won't go into the details of this because this is a little bit involved, but we have a supplementary information in our publication that's 50 pages long that goes into a lot of details of this signal machine learning processing. Then we have amplitude features, where is the peak of the bioimpedance, the minimum of the bioimpedance. We also have area features, the area under the curve. All of these parameters are then, or features, are the inputs to the machine learning network. So we have all these inputs, this hidden layers or hidden correlation that we just don't have enough understanding about. So for machine learning, it's no big problem. You can do the, in this case, convolutional neural network. And then the outputs that we seek are the systolic and diastolic, beat to beat, so the maximum and minimum. So how do you train this? So first of all, we have to implement in hardware. So for the hardware, as I mentioned, we have this ulnar and radial arteries. We have these channels. And these channels, we measure the voltage. You apply current, you measure the voltage. It's also shown below. So the normalization of the voltage to current gives you the bioimpedance. And then from the bioimpedance and the transit time delay, you can extract all these features that I mentioned in the previous slide and feed it into a convolutional neural network. You do the feature extraction. Then for those that are familiar with machine learning, you do so-called ADA boost regression to improve the accuracy and the outputs of this systolic and diastolic blood pressure. The way it actually connected to the hand is shown below. In terms of the front end electronics, you basically have these bioimpedance channels. You feed it to an instrumentation amplifier. Instrumentation amplifiers are very standard electronics where you want a very high common mode rejection. So a lot of common mode noise can be rejected. It has a very high bandwidth. And then this is a differential instrumentation amplifier. And then after that, you feed that to integrator. Integrator is also a very popular electronic block. You often do that before you do analog to digital conversion. So when you feed that into the integrator, then you can do your analog to digital conversion. This is a very simple ADC electronic 4-channel because these signals are very slow. You just need a basic 24-bit type of ADC. So I won't go into the details of this, but a lot of that for those in electronics, they can find it in the journal paper. So training. The accuracy of a machine learning network depends on the robustness of the training procedure. So we implemented different training activities to determine the most convenient and the most accurate way to train the network to get clinically accurate conversion of bioimpedance to blood pressure. So one training is the so-called cold pressor hand grip. So you squeeze a hand grip that then of course exerts pressure on your arteries. So your blood pressure here shown is the blood pressure. It goes up. This is the systolic and diastolic. This hand is gripped for about 3 minutes, so the blood pressure goes up. And then after 3 minutes, you put the hand in an ice bucket, so that stabilizes the blood pressure at the high level. And then you rest. You take your hand out of the ice bucket after about a minute to rest it, so it begins to cool down, and then the blood pressure goes down. So these are all exercises to elevate the blood pressure over a wide range in order to be able to train this network so that it can convert bioimpedance to blood pressure over also a wide range. So this is one training activity. Another activity to elevate the blood pressure is exercise, in this particular case, cycling. Again, when you begin the cycle, it takes a while for the blood pressure to begin to increase, but then, finally it begins to increase. This is cycling for about 4 minutes. And then when you stop cycling, actually the blood pressure dramatically relaxes back very quickly. So that is an exercise activity. You can repeat this many cycles. And then the last one is the Valsalva. So Valsalva is a very popular way to kind of unblock your nose or your ears. People that do scuba diving, for example, I'm a certified scuba diver. I do, and we do Valsalva all the time when we're underwater to unblock. So with the Valsalva technique, when you have to pinch your nose, then you build up pressure. So then that leads to this spike in the blood pressure, and then you blow out through the mouth. So when you blow out through the mouth while still pinching your nose, then that releases the internal pressure that built up. And then because you're still pinching your nose, when you start blowing out, pressure builds up again. And then finally you release your hand from your nose, you stop pinching your nose, and you grab the blood pressure then begins to relax. So we did all of these training exercises, and the one that is best for the neural network is the cold pressor end grip. And that is because you have a smooth, more or less a smooth increase of the blood pressure from the low to the high, and smooth decrease of the blood pressure from the high to the low. So you want very smooth, as much as possible, linear variations, and this is very good for the machine learning network. In the cycling case, you have this abrupt region, so that affects the accuracy of the machine learning. And in the Valsalva case, you can tell that you have more complex waveforms, and so that requires a lot more sampling in order to build a robust network. So altogether, the cold pressor end grip is the best for the training exercise. So after you do this training, then you can measure the blood pressure, the bioimpedance of many subjects, volunteer subjects, convert it to blood pressure, and then we get this measurement of the systolic blood pressure, the diastolic blood pressure for different subjects. And then how do you quantify the accuracy of this recordings? So fortunately, the IEEE organization, and I'm delighted this is more or less an IEEE colloquium or symposium, the IEEE has released a standard for quantifying the accuracy of wearable blood pressure technology and other wearable devices. So there are three categories. There's the grade A, grade B, and grade C. All of these relate to the absolute of the mean error and the standard deviation of the measurement. So grade A is the highest accuracy, clinically accurate recordings. Grade B is less accurate, and grade C is even less accurate. So the technology that I'm reporting here, the bioimpedance, this is in grade A category. So it's clinically accurate blood pressure recordings. There are other options also in grade A, but I'd like to highlight to you that the one that we're reporting here also has advantages that are not captured in the accuracy metric. And these advantages includes the fact that it's continuous. We can do heartbeat to heartbeat recording over time. So most of these other technologies, the Omron, the Cuff, for example, those are not beat to beat. You have to, it takes, some time to collect one data, so you can only do a limited set of recording in a given period. Another advantage is we can do dynamic recording. So when the subject is eating, when they're doing exercise, the blood pressure can still be collected beat to beat. And so this is not possible with many other technologies at the moment. Besides the blood pressure, another very important vital sign is respiration rate. So that's more or less your breathing rate. So that's a very critical vital sign. Normally you want your respiration rate, how many breaths you take in, per minute, breaths per minute. Should, for normal healthy subjects, should be somewhere between, let's say, 12 to 18. So we can also collect this automatically from this graphene electronic tattoos. And so shown here is the respiration rate of a subject, and a zoom in shows the cycles, the bioimpedance cycles. You can do a Fourier transform of these signals to find the frequency of this signal. So when you do that, it's around 0.3 hertz. That's exactly what you expect for breathing, healthy breathing. That corresponds to about 12 to 15 breaths per minute. So this comes for free with this electronic graphene tattoos. As you measure the bioimpedance, you can measure the blood pressure, you can measure the respiration rate, you can measure the temperature, you can also measure all the electrophysiological data, you can measure the skin hydration. So you can get all of this data relating to the health and the well-being of a human with this electronic tattoo technologies. So right now, many of our recordings are still tethered. Especially the blood pressure is new research that we just developed and published. So we're now thinking, how do we convert this to completely wearable and wireless? So the electronics all have to now be converted to a wearable chip. There are two ways to do this. One is you have a smart patch or band. So this is just an illustration. This is not our work, just some illustration to show the concept. You have some electronic chip. This chip has the signal processing, data transfer capabilities, and then you have some graphene tattoos, and you combine everything into a smart patch. Another one is to have a smart watch, and the smart watch, you can put the graphene tattoos around the wristband and then collect the data, and then all the signal processing can be done in the electronics in the watch. So we're looking at these two platforms for further development towards wireless, fully wireless wearable technology. What are some of the potential integration for wearables? So I'm going to focus on the metaverse. So some of you may be familiar with the metaverse. The metaverse is now becoming more and more a popular platform. Today, the metaverse is dominated by entertainment, right? Playing games and stuff. But in more recent time, people have begun to think about meta health, using the metaverse for health. So today's, augmented or virtual reality medicine is telemedicine. So this is where you have a video appointment with your doctor, for example, and this became very popular in the pandemic for obvious reasons. And it also has the benefit that people could access perhaps a greater collection of medical professionals through this video appointment system. Of course, it faces challenges because the medical doctor does not have live access to your medical condition or medical recording or medical status. For this kind of platforms, you have to go to the clinic and do some laboratory testing, and then you come to see the doctor by video appointment, and then you can discuss the results. So it's better than nothing, but it's not of the same value as an in-person visit where the doctor can do some direct measurements on you. So meta health may also be the next evolution of remote monitoring. So if you're monitoring subjects, older subjects or patients, for example, being able to access their data remotely can give you an idea of their progress on the treatment. Meta health could also be a next iteration or future version to help manage stress and fatigue, especially with data like blood pressure. Then that could become very useful for medical professionals to advise their patients. So we've started thinking about how to use these wearables for meta health, and the idea is to go beyond today's telemedicine. So in order to do that, in this metaverse, let's say you have a metaverse meeting, the doctor or the medical professional can have immediate live access to wearable data of their patient. So this wearable data would include all of the electrophysiological data, ECG, EEG, EMG, and all of the vital signs, respiration rate, oxygen level, and very importantly, the blood pressure. So if they could have all of that data while having that meeting with their subject or their patient, that would transform that to something very similar to in-person meeting. So we're now exploring, actually in collaboration with people that do metaverse research, the idea of a metaverse physical checkup. Instead of a normal physical checkup in person with the doctor, can we deploy our wearable sensors, all that data being collected from the patient, for example, then can be fed into the metadata stream. And this metadata stream between the patient and the doctor, the patient meta stream will contain all the wearable data, health data, and the doctor will be able to access all of this in that meeting on their meta gadget. Often the meta gadget is just the goggles, right? So they can see all of that, and then it's more or less similar to what you have in person, right? When you go in person, the doctor collects all of this data and then is able to interpret the data and then make some recommendations for health to improve well-being. So that's an idea that we are very keen to demonstrate using our wearable platform and having two subjects, a patient and a doctor, show the possibility of transferring this wearable data stream into the metadata stream between two people. So I think there's a lot of opportunity for wearables for meta health, and I'll be very happy to discuss that with others that are interested. So I've talked a lot about graphene-based sensors, and in particular on wearable health. I mostly focused on non-invasive applications. This picture is taken from a very, very nice review by my very esteemed colleague, Li Tao Son from Southeast University in China. So graphene can be used on the skin. This is epidermal or tattoo sensors for measuring, all of these parameters. I didn't mention really any on biochemical, but you can also do biochemical sensing on the skin, and you can use that, for example, to monitor dopamine, which is a marker for stress, for example. So a lot of opportunity. I know there may be students in the audience. You can consider this area as very innovative area for research and development. And then there are also applications that are invasive, where you put the graphene or 2D materials inside the body. And that can also be very useful for many, many medical applications. We are also working on invasive applications of the graphene. And I'll just highlight just one example, which is using graphene electrodes placed on the heart for in vivo diagnostic and treatment. In this particular case, the disease is arrhythmia. Arrhythmia is a condition where you have an irregular heartbeat, and this by itself is responsible. It's a cardiovascular disorder, so it's responsible for 15% of global deaths. So all of this technology we're talking about, technology, wearable technology, have it can have great massive impact on our lives, on global health, preventing deaths, extending well-being, and so on. So these are very, very high impact opportunities for using these materials. So I won't go into the details of this. Needless to say, this experiment was done in a live animal, and then rat. We place the graphene tattoos on the heart so we can monitor the in vivo ECG. It has all these features that you see that are the normal features, and then you can find out if they're irregular heartbeats. And so when you have irregular heartbeats, for example, you can observe it, then you can stimulate with the graphene. So you can apply voltage And when you stimulate with the graphene, you can then treat this condition and the heartbeat can become regular. So the basic idea is with graphene electrodes, you can diagnose regular heartbeat and also stimulate to treat the irregular heartbeat. So this is under review. I won't discuss it in much detail right now. So I would like to now conclude and thank my collaborators and of course the wonderful group of postdocs and graduate students and undergraduates that have worked on this research, and then our sponsors that have supported the work. A lot of what I've discussed, the majority are in this paper is shown here. The blood pressure work is the one in Nature Nanotechnology. Then we have graphene, brain-inspired electronics in Nature Communications. The arrhythmia in vivo studies is under review, but it's actually also on archive, so it can be accessed if you just search my name or email me. I'll be able to share any of this work with you. And then my website has some more detail on different television interviews and magazine interviews that we have done, especially on the blood pressure and the electronic tattoos. So at this time, I'll be very happy to take any questions. So do feel free to ask your questions.
Thank you for this nice presentation. And there's a question, actually two in one. It's from Professor Marcelo Pavanello from FEI in Brazil. And he says, thank you for your nice presentation. Could you please comment on the longevity of the graphene tattoos and the reuse of them? Also, could you please comment on the variability between measurements done in the same person using different graphene tattoos?
Yeah, those are very, very good questions that we addressed in our publications. So the longevity of the graphene tattoo without any adhesive, if you just put the graphene tattoos on the skin, it will last, depending on the person, let's say 3 to 5 days. And we've done tests in which the signal is of high quality in that period. And the 3 to 5 days, the subject is doing their normal everyday activities. They're taking a shower, once a day or twice a day. Of course, they're not scrubbing their skin. They're using liquid soap in the case of taking a shower or a bath. And so it lasts 3 to 5 days. And then if you spray a liquid bandage, so they spray on liquid bandage, then you can extend it and it can last up to a week. So these are not permanent tattoos. They're temporary tattoos. Then in terms of the accuracy of the signal, let's say you place the graphene tattoo on one subject, you did the machine learning training on that subject, and then using that machine learning training from one subject, you place the tattoo on a different subject. In that particular case, instead of getting a grade A accuracy for the blood pressure recording, you'll get a grade B accuracy for the blood pressure recording. So it's still very accurate in terms of blood pressure recording and very useful. We think that it may be possible to improve the machine learning algorithm better. And so that is still research in progress.
Thank you. Yes, thanking you too, Professor Pavanello. Oh, any other question from the audience? You can type here on the chat, or you can move to the orange icon and speak. I don't see any other questions, so thank you very much. Oh, there's another one. Great talk. It's Professor Marcilei from FEI in Brazil. Has this material been tested for tolerance to the effects of ionizing radiation? This use proposal implies being subjected to different environments that can change the functionality of the sensors. We know that small changes in the crystal lattice of this material compromises its properties.
Yes, ionizing radiation, the short answer is no. They have not been tested or subjected to conditions of ionizing radiation. Since we're focused on mobile and wearable health, I don't think that everyday people wearing this will be exposed to significant or measurable amounts of ionizing radiation. So for this reason, we have not done any tests. Of course, if they're in a clinical environment doing X-rays or whatever ionizing testing, then there's a possibility of exposure. So we've not considered that actually. So thank you very much for that question.
Thank you, Deji. No? Any other question? If not, thank you very much, Deji, for your very nice presentation. It's a very interesting subject. So we thank for your participation on behalf of the organizing committee of the conference, but also from the student chapter, the Electron Devices Society student chapter here. And thank you. And we will keep in touch. I will have a look at your website and the nice videos that you mentioned.
Thank you very much. It's a pleasure.
So with this, we conclude the morning session of the tutorials day. And I invite you to come back at 1:40 in the afternoon for the presentation, for the first presentation in the afternoon. Let me just put here to show you that will be Trends and Challenges in Nanoelectronics for the Next Decade, given by Dr. Elena Gnani. So have a good lunch. Laranjinha, isso habilita o microfone das pessoas. Então, se alguém quiser fazer pergunta por voz, tem que vir aqui. Então, sobe aqui, por favor. Marceli?
Ah, vi.
Aí todo mundo vai te ouvir.
Entendi, entendi. Aí, quando eles perguntarem, eles vão enviar no chat para mim. Eu tenho que ficar de olho no chat. Tá. É, porque não, o pessoal deve estar perdido que nem eu. Uhum. Mas quem compartilha sou eu ou são eles? Tá. Hum. Ah, eu tenho que avisar eles. É, mas é bom eu saber. Ô, Michele, deixa eu fazer uma pergunta. Eu vou ser chair na quinta tarde. Você não tem um tempinho, qualquer outro horário antes de quinta tarde, para junto com você olhar a tela e ver o que eu vou fazer? Não, é que agora eu dou aula, 1h40, se eu não almoçar não dá tempo. Não, não, nada. Onde eu estou. Por exemplo, assim, Dear Michelle, please share your... Ok, tá. Onde que ela vai ficar? O palestrante fica onde? Num dos azuis também. Ele vai ficar perto de mim. Tá, tá. Entendi. Hum, entendi. Tá. Mas eu em si não tenho que fazer nada, é só o papel de chair como se fosse presencial. Eu vou chamar, vou fazer as questões, vou ler as questões e tudo bem. É isso? Ah, sim. Não, não, tranquilo, tranquilo. Ai, obrigada, amiguinha. Eu quero uma... Então, você viu, eu queria ser loirinha. Hã, hã, hã. Hum, tá, vou fazer isso numa hora que eu possa brincar disso. tá? Obrigada, Mi. Tá, beijo. Tchau.
Michele. Okay, so good afternoon to everyone. So let's continue our EDS mini-colloquium. And the next tutorial, entitled Trends and Challenges in Nanoelectronics for the Next Decade, will be presented by Elena Ignani. This presentation will be transmitted by the YouTube of SBMicro. Elena Ignani is Associate Professor at the University of Bologna. Her research interests include the development of physical transport modules in semiconductor devices and numerical analysis techniques, with special emphasis on the study of quantum-confined devices such as FinFETs, silicon nanowires, steep-lobe devices, as well as quasi-ballistic transport in MOSFETs. Elena is the author or co-author of more than 180 papers published in referred international journals and in proceedings of major international conferences. She is presently an IEEE senior member, IDS distinguished lecturer, member of the IDS Technology Computer and Design Committee, and serves as an associate editor of the IEEE Transaction on Electron Devices. Thank you, Elena, for joining us in this conference, and feel free to start sharing your screen and start your presentation. Thank you.
Thank you, Renan. Good afternoon. First of all, can you hear me?
Yes.
Okay, so I try to share the screen. Do you see the presentation?
Yes, yes.
Okay. Now it should be in presentation mode.
Yes, I can see it.
Okay, perfect. So first of all, I want to thank you for your kind invitation to deliver these lectures. My lecture will be an overview, I would say, of the trends and challenges in nanoelectronics for the next decade. This is the outline of my presentation. I will give an introduction regarding the scaling and the Moore law. We are discussing of new emerging devices, so we cannot avoid giving an introduction on the scaling of, I would say, conventional classical devices. We will see the improvement that we got by scaling the devices. We will go deep in the discussion of the nowadays key issue regarding the scaling of devices that is related to the power that is consumed by our devices. And we will see the emerging devices that are now under investigation, that have been proposed in the literature to overcome the major scaling roadblocks related to conventional devices. We will see a benchmark between all these devices, and we will conclude with some prospects and challenges. So the Moore's law, probably everyone here in the audience has heard something regarding the Moore law. Gordon Moore, that is very famous guy by Intel, that funded Intel, predicted at the beginning of the 70s of last century that there would be a doubling of the number of transistors per chip every 2 years. This law was more or less, I would say, an empirical law, and was related to an economical overview. So he realized that reducing the size of the transistor would reduce the cost per transistor. So economically, it was favorable for foundries to scale the devices. And we see that more or less all the major fabs followed this law that is in logarithmic scale. So a line in logarithmic scale implies an exponential increase, that is this 2 times the doubling of the number of transistors in a logarithmic scale is is reported, gives a linear trend. But we can come back even earlier in time, because the Moore's law is related more or less to the 60th century, but we can say that the beginning of electronics started even earlier, much earlier. We can say at the beginning of last century, where we started electronics with electromechanical switches, then we moved to solid-state relay, to vacuum tubes, and we had some devices, some systems able to make some calculation. And but the real breakthrough that we saw historically came out with the invention of transistors. That was invented almost in the 50s of last century. From then, we had really an exponential improvement of the calculation of the number of operations that we could achieve for each second. And we can say that in principle, if we follow this trend, if we continue to follow this trend, we could say that in 20, 30, probably years, we could in principle get devices able to reach the capability, the calculation capability of the human brain. So everything started taking advantage of the scaling of devices. What are the famous scaling rules that were published by Bob Denard in the 70s of last century? Mainly, the idea is that you start from an original device, you scale the sizes, so you adjust the dimensions and the voltages, the doping, in order to achieve smaller FETs, but with the same electrostatic behavior, so with the same electric field inside the device. That would give the same current, as you can see from the left to the right, the same current with a device that is smaller. So it's, in principle, it is really a breakthrough, because you can reduce the area without losing in performance. So the idea is that you scale the voltage, you scale each length of the same factor. You need to scale also the junction depth, and what you get, if you make some very easy calculations, is that you reduce the current, you obviously reduce the area with the factor that is alpha to the power of 2, you reduce the power, but what you get is that you improve the performance, so your delay is reduced by a factor of alpha, so your device is faster, that is very good news, and then you keep constant, in principle, the power density. So the scaling at the end would give an improvement of the performance. That is the reason why, so you reduce the cost of each transistor, you improve the performance, so that was the reason why each foundry followed these scaling rules. That is an idea of how far scaling went in the last century. That is a micrograph of an SRAM cell of 1980, and you see that in 2011, an SRAM in the 22 nanometer node technology node was much, much smaller, all the SRAM cell, than a single pad that we had in an SRAM cell of 1980. You see, really, that is the small, complete SRAM cell. That is much, much smaller than one single pad. That was provided by scaling. This scaling allowed not only a performance improvement, in principle, we should get a performance improvement. So if we follow what is called more scaling, we move towards technology nodes, but also widened. So the application. So we got more application. You see that now the devices are not only used for computation, okay, for microprocessors, so standard computation, microcontroller, but also we had experienced a widening of the application market. So now we have devices for analog calculation, we have devices for memory, for artificial intelligence, for power, very important market. Now we have a lot of calculation, we have a lot of research on sensors and actuators, and also the application, the biomedical application. So we widened the possibility of research, I would say, of young engineers, because we do not have only one target, that is to improve the performance of the microprocessor, so the computation unit, but also the application to really a wide spectrum of applications. Now let's look a bit deeper regarding the performance improvement that should be given by scaling. So probably we all know that we had to experience in the last 20 years some roadblocks that prevented or made harder the scaling of devices. For example, it is quite difficult to scale with the same factor the oxide thickness as the gate length, because if you reduce the oxide thickness, you exponentially improve the gate leakage. In order to prevent this exponential increase of the gate leakage, what we invented, I would say what electrical engineers invented, was the introduction of the high-K dielectrics and metal gate stack in order to use a thinner oxide with the same electrical oxide thickness as the standard, I would say, one of SiO2. But this different scaling of the oxide thickness and the gate length caused what are called the short channel effects. That means that you have short channel effects are, for example, the threshold roll-off, so the dependence of the threshold on the drain voltage, or the degradation of the slope in subthreshold, or for example, the drain-induced barrier lowering, so the variation of the current in subthreshold as a function of the drain voltage. So the drain voltage affects the height of the potential barrier. In order to overcome these roadblocks, new device architectures were proposed. So we moved from planar devices mainly to three-dimensional devices like FinFET, and we introduced also high mobility channel materials, for example, germanium or other exotic materials, so investigated in order to improve the short channel effects. We introduced also, for example, strain as a current booster to improve the performance, so the performance, so the throughput of our devices, of our circuits, introducing strain in the channel, taking advantage of strain and high mobility materials. We need also to take into account that if we move to small sizes, we need to take into account that we have an increase in parasitics. We have an increase in statistical variations that are related to fabrication process. So fabrication becomes much more difficult, more engaging. Then we need to take into account quantum effects. And at the end, when we move to sizes that are of the nanometer, in the nanometer scale, we need to take into account the atomic position of each atom and the atomic details of our semiconductor that we investigate, because if we really want to get the correct performance of our device. So we cannot neglect the fact that we are moving to systems or devices where we have a few number of atoms. So scaling now requires really continual innovation in transistor structure and material. So it has become really a very, very difficult, engaging stuff. These two figures, for example, show the projected scaling of IRDS, International Roadmap of Device Semiconductor Devices. On the left, we see the scaling of some sizes, for example, the pitch, the gate pitch, the gate length, the device lateral pitch as a function of the years. And you see that if we focus on the green curve, that is the easiest one to understand, that is the gate length, you see that it is predicted that in 2028, we will see a stop, a saturation of the scaling of the gate length. So the gate length could not move to values lower than is predicted, that would not be able to move to sizes, to lengths shorter than 12 nanometers. If we look on the figure on the right, that is again a prediction. I want to point out that point. What we see is that in principle, if we look to the CPU throughput at the maximum frequency, in principle, our CPU could improve the throughput because we could in principle improve the frequency, so our devices would be able to improve the performance. But we need, if we plot the CPU throughput at a constant power density, so if we want to keep the power density, I want to point out this, so the power for a fixed area constant, we need to stop the improvement, so to reduce the frequency of our microprocessors in order not to improve, to increase too much the power, the power consumption. So we have now thermal constraints that are caused by the increasing power density. So the CPU needs, in principle, to be throttled more frequently to maintain the same power density. That is really not a good news, this one. We need, in principle, this graph shows that we should be able, in principle, one moment, we could be able to improve the performance or to increase the frequency of our microprocessor, but we need to stay fixed at a fixed frequency in order not to get a too high power density. Just a recap of what happened in the last 20 years. I would say that we will see this graph as a major disruptive invention that we had in the last 20 years. The first one was the introduction of copper as interconnects. Instead of aluminum. Then another breakthrough was given by the introduction of strain in the channel, strained channel, in order to improve more the mobility of electrons and holes in different way for electrons and holes. That we had at the beginning of this century, the introduction of the metal gate, high K metal gate stack, in order to reduce the leakage current. Now I would say that the gate leakage is not a major problem in conventional devices. But the disruptive invention was the transition from planar devices, that is a wall. I would say that here we have a wall. We moved from planar devices, all the one on the left, to three-dimensional devices that are FinFET. In 2010, more or less, Intel introduced the FinFET, a three-dimensional device, so moved from planar to a three-dimensional structure. Now, the research And the market is focusing on nano sheets. That is an improvement, I would say, of the original concept of FinFET. Now, what we can say is that nowadays the scaling paradigm is no more the original idea was that we need to scale the sizes and the voltages. Okay, now the scaling paradigm needs to take into account the area, obviously, the cost, as was in the past, but also the performance, obviously, but the key, the first word now that we have here is power. Power is now the key figure of merit that we need to take into account when we want to scale our device in order to improve the performance, ideally. So we see, again, this is a figure of the IRDS. So it's a prediction. So the prediction was that we had the FinFET. We already have our devices that are circuits that are realized with FinFET. The idea is to move to gate nanowire that are these structures, gate all around horizontal nanowires or nanosheets. So the prediction is to have nanosheet in production in 10 years, more or less. Then we can move also in a vertical way, in a vertical direction. So we have the transport that is no more planar transport, horizontal one, but a vertical one from source to drain. This approach is already used for memories, for NAND memories, for example. And again, an additional idea that could enter the market in, I would say, 10 years or 15 years is the idea to stack one over the other different many devices. So, for example, many nanowires or many nanosheets, one over the other one. So to take advantage of the third dimension, not only in the sense that we can put more nanowires one over one on the other one, but put many devices realized with nanosheets one over the other one. So we can say that we have experienced three different ages of scaling. We can say that in the last century, we had a very simple geometrical scaling. That means that we experienced, we reduced the horizontal and vertical dimensions in conjunction, and this would gave an improvement performance of planar transistor. What we experienced in the last 20 years is what is called equivalent scaling. So we saw a reduction of only the horizontal dimension and not the vertical dimension, in conjunction with the introduction of new materials, for example, germanium, and new physical effects. So we took into account also new physical effects. We need to take into account quantum effects, for example, quantum confinement. And we moved from planar devices to vertical devices like FinFET. What we will see in the next years is called 3D power scaling. So the transition, we will see the transition to complete vertical device structures. We will see an heterogeneous integration of different materials in conjunction with, in principle, the idea is to reduce the power consumption in order to be able to improve the performance of the device, reducing the power consumption. So the power is, so now the key figure of merit that we need to take into account before trying to improve the performance of the device is to reduce the power consumption, or at least to keep constant the power consumption. So we need to discuss the power problem of integrated circuits. There are many causes of power consumption, obviously, within big systems, complex systems. But the power is given by devices. So, which are the power, the two major power power contribution, the two major contribution to the power consumption of devices. We have what is called leakage power and the active power. The leakage power is the power that is delivered when the device should be off. So I always say to my student that is a bad power, because it's the power that you deliver when you are doing nothing, no computation. The device should be off. So it's doing nothing and you deliver power. So you have a power dissipation. Then we have the active power, that is a power that is delivered when you make a calculation. So in principle is I would say, good power, in the sense that at least you deliver power, but you are doing something. That is a very famous graph from Intel that shows these two contributions. So the red one is the leakage power density, and the blue one is the active power density as a function of the gate length. So if you move from right to left, you scale the gate length, and you see that you increase the leakage. This graph is in logarithmic scale, so again you have an exponential increase of the power dissipation. Note that according to the Denard rules, the scaling rules, the active power should be constant as a function of gate length. So we should see something that is of that kind, constant. Whereas in reality, you see that we have a slight increase of the active power. But the really bad news is this one. So if you scale the gate length, you have an exponential increase of the leakage current with a slope that is very, very high. You see that at this point, at this gate length that was around 90 nanometers, channel length more or less, you had a cross between the two lines, so the leakage power becomes higher than the active power. So you have, at the end, the majority of the power that you are delivering is consumed when you are doing nothing. So there are many contributions to this leakage power that are given by the gate leakage that now has been reduced, has been almost eliminated in our circuit thanks to the high-K metal gate stack. Then we have the junctions that are in reverse, very small contribution. The major contribution is the off current from source to drain that we have when the device is off. That is related to the length, okay, to the gate length. The shorter the gate length is, the higher the probability we have to have a tunneling current from a direct tunneling current from source to drain. So now the transistor scaling focuses on reducing the leakage. Now let's look. So in principle, also the active power. So now let's look inside the two contributions, the leakage power and the active power. The active power is proportional to the load capacitance and the supply voltage square. Okay, to the power of 2. That means that if you reduce the supply voltage, you obviously reduce the active power. But if you want to reduce the supply voltage, keeping constant the performance, you need to keep constant what is called the gate overdrive. That is the difference between the VDD, I would say, and the threshold voltage. So this window must be kept constant. So you see that if you scale the supply voltage, this point shifts towards the left, moves here. You want to keep constant the on current, that is this value, okay? And you need to keep constant this window. So you need to shift of the same quantity, the threshold voltage, so to move this point towards the left. But if you shift this curve, that means that you shift this curve towards the left. If you shift this curve towards the left, what you experience is an exponential increase of the current at 0 gate voltage. That is the leakage current for definition, the current at 0 gate voltage. So if you want to reduce the active power, or to, in principle, to reduce the active power, you need to reduce the supply voltage, you need to reduce the threshold, so you have an exponential increase of the leakage current. That is an exponential increase of the leakage power. So remember that you reduce the active power if you reduce the supply voltage, but if you reduce the supply voltage, you increase the leakage power. So in principle, what the optimum device should be able to deliver the same on current, like this one, with the lowest, as low as possible leakage current in the off state. That would be I would say an ideal device that would reduce both the active power, keeping constant the leakage power. So now if we plot the two power or the energy contribution, so the dynamic energy and the leakage energies that are related to the power, what we see is that the dynamic energy is proportional to the supply voltage V square, VDD square. That means that if we increase the VDD, we get a curve like this one, that is the green curve. So we have an increase of the active energy as a function of the supply voltage. Whereas, remember that what we have seen before, if we reduce the supply voltage, we have an exponential increase of the leakage energy. That is what we see here. Sorry. If we reduce the supply voltage, we have an exponential increase of the leakage energy. The total energy is obviously the sum of these two contributions. That means that we have to sum this orange curve with the green curve. We get the red curve, and you see that the sum of these two curves, this gives a trend like this one. So we have a minimum. So there is a minimum supply voltage below this that gives the minimum energy. So if we use a supply voltage that is lower than VDD, in principle, we reduce VDD, but the energy per operation would increase. So it is a nonsense to use a VDD lower than this value. So there is a fundamental lower limit. Now let's look to the graph on the right. What we see in the graph on the right is that if, in principle, we would be able to shift this leakage, this dotted orange curve, that is the original one, that is the energy, towards the left, so to reduce the leakage energy towards this curve. Again, if we sum this new orange curve with the green one, okay, what we get is that we get this solid red curve instead of this dashed, and we see that here now in this hypothesis, what we get is that we could reduce the energy per operation with respect to this case, and also reduce the minimum. So we can reduce the minimum supply voltage that we can use, reducing also the energy per operation. So now the target is to be able to find devices able to reduce the leakage current. So all the devices that have been proposed to solve in the literature to solve this problem are called, I would say, beyond CMOS devices. So what does it mean beyond CMOS? Beyond CMOS, in principle, refers to potential future digital logic technologies, in general, technologies, I point out this one, that expand beyond the present CMOS scaling limits. So the idea is to improve what can be achieved using conventional CMOS approaches, I would say, in order to open, the idea is to open a new era for computing. So beyond CMOS is focuses, I would say, on three pillars. New memory technology, that there is now I would say only 2 words on that. New memory technology, there is really a huge research on such pillar, because there is now a new research on devices able to realize neural networks, for example, that are memory-based devices able to realize neural network that are on the, I would say, that are on the word memory. Then we have new logic devices, that means new materials and new device concept to replace silicon or invent something unconventional in order to get new computing paradigms. And then we have obviously new also approaches related to architecture, so inventing new information platforms, for example, given by heterogeneous integration of different systems of multifunctional components. In this presentation, I will focus on these pillars, so on devices, but remember that there is really a lot of research also on these 2 other topics. So now, what is a device? So I will focus on logic devices, but what is really a device? Now we need to come back to fundamental information. What is a device? A device is a component that should provide the physical means for representing and manipulating a computational state variable among its 2 or more allowed states. We all know bits, the 0 bit and 1 bit. A device should be able to represent this 0 bit and 1 bit, and also to manipulate these 2 bits in order to move from one to the other. Okay? The important point, the important word is a computational state variable, because you can represent this bit in different ways. So the taxonomy of emerging logic devices can be described according to this graph. So on the x-axis, we have structure and materials. So we can have devices with conventional structure or using conventional semiconductors like silicon, for example. Or we can move also to novel structures or materials. On the y-axis, we have the state variable. The state variable is the way, okay, in which we encode the computational state, the bit, okay? We could use the charge, for example, in a conventional CMOS MOS device, the 0 bit is no current, no charge, whereas the 1 bit is we have a current, we have the charge in the channel. So the state variable in conventional charged base, it could be charged base like in conventional devices, or non-charge. There are many devices that are now proposed in the literature based on spin. For example, spin is not a charge. The information is spin up or spin down. So 0 and 1 are encoded, the bit 0 and 1 are encoded with the spin up or the spin down. So all devices can be put in this graph. So if we have conventional devices that use the charge as a state variable are devices, all these devices that are in this orange rectangle extend the classical MOSFET to the end of what is called the end of the roadmap. So follows the Moore's law. If we have novel materials, novel device structures that where still the state variable is the charge, we have what are called non-conventional FETs and other charge-based information devices. Whereas in this purple area, we have novel, I would say exotic and novel exotic devices where the state variable is no more the charge. We have what are called alternative information processing devices. Just put some name in this graph. Conventional, I would say we all know fully depleted SOI, horizontal gate-all-around nanowire, vertical gate-all-around nanowire, FinFET, CNT FETs, all these devices are what I would call almost conventional devices that we have seen that are also someone are also in production. Nanowires are in production for memories, for NAND memories. Then in this rectangle that are the non-conventional FETs, we see devices like tunnel FET, impact ionization MOSFET, NEMFET, MOTFET, negative capacitance FET. We will discuss these devices where again the transport mechanism is different from the classical thermoionic emission over the barrier, but again the information is stored with the charge. I have no charge in the off, or I have the charge in the channel in the on state. Then we have the devices that are based on magnetic field or spin, that are, for example, the spin FET, the spin transfer top logic, the spin orbit torque. We have, for example, or devices for quantum computation. Before giving a discussion of a description of all these devices, okay, I will not focus on almost conventional devices. Again, I want to point out some key concepts that we need again to take into account, that there are requirements that each device must satisfy in order to be considered as a device that can replace conventional CMOS. For example, you need to get a non-linear behavior, okay, in order to be able to achieve a good noise margin. You need a power amplification, so you need to have a gain larger than 1. You need to prevent, since you want to make calculations, so you want to put logic gates one after the other, okay, you need to prevent feedback, that the output should not affect the input. You need to be able to realize a complete set of Boolean operators, the not, and, or equivalent, whatever you want to use. You need to be able to realize a concatenation of these devices. The output of one device should drive another logic gate. Then you have physical requirements, so the device should be scalable. Otherwise, you will never use this device. Should be fast, and in principle, the power should be lower than the one of conventional devices. You have also technological requirements. In principle, it should be a good news if it would be able to operate at room temperature and even higher. Should show a low sensitivity to parameters, should be reliable, should be compatible with CMOS, because the idea is to make a heterogeneous integration of non-conventional and conventional devices. Should be also CMOS process compatible. And also the parasitics should be small. So a solid-state device needs to satisfy all these requirements before it can be considered as a candidate for an element of an integrated logic circuit. So now let's move on the discussion of some of these devices that sometimes some of these emerging devices offer fundamental different and unique characteristic. And sometimes this unique characteristic allow the designer to invent non-traditional circuit concept in order to realize their full potential. Now, starting from the computational variable, okay, for classical devices, the computational variable is the charge. So we have as I told you before, obviously the variables are the current, the voltage, and the charge. But you could also take advantage of the electric dipole. For example, in ferroelectric devices, ferroelectric FET, you have a dipole, an electric dipole, and the 0 bit is with the dipole towards the down. So dipole down, electric dipole down, whereas the bit 1 is stored, the variable is the dipole up. The same as spin, so a magnetic dipole, so you can take advantage of spin up and spin down to to represent, to encode your bit. Or for example, in the position, we will see that the position of a cantilever, for example, of a beam, can store the bit 1 or the bit 0. Again, if another point that we need to take into account is that we need to realize a concatenation. So the output of a device need to be the same computational variable as the input of the next device. That is always, for us, it's immediate, because for conventional devices is always the case. So you drive the device with a voltage, you have the input that is a voltage, and the output is a voltage. So you can concatenate without any problem logic gates. But for example, when you start using spin and magnetic fields, you need to take into account that, for example, in magnetic devices, you need to convert the current in magnetic field, okay, and then again the magnetic field should be converted in current in order to create a concatenation. So sometimes you need a transducer. Again, also if you use the spin according, if you have a magnetic switching or spin torque switching, you need to convert the voltage in a magnetic field, and then magnetic field in a current into a current, and then into a voltage. So in this case, if the device enters with magnetic field, but you need to drive it with a voltage, you need a transducer between each gate, and you need to take into account when you investigate the performance. You should not only take into account the performance of the single device, but also you need to take into account that you need transducer that obviously contribute to the power, to the delay of your final circuit. So let's focus on non-conventional FETs, but still charge-based devices. So for this kind of devices, the idea is that let's start, we want to reduce the power, so we want to reduce the leakage mainly, so our driver is this one. So in conventional devices, in standard CMOS devices, we all should know that if we increase the gate voltage, we reduce the voltage, the potential barrier in the channel. So we increase the number of carriers that can be emitted from the source to the drain by thermoionic emission. The physical mechanism is the thermoionic emission over the barrier. So you increase the gate voltage, you push down the potential barrier, you exponentially increase the number of carriers that are able to flow from the source to the drain, and you have this exponential increase in subthreshold of the current. The slope, as we all know, is the inverse of the derivative of the current as a function of the gate voltage. So we can split this ratio into terms. So we can say that we investigate. So this ratio is given by two terms. The derivative of, let's look at the inverse, the derivative of the surface potential, that is this value, the potential barrier at the surface, as a function of the gate voltage. That means in which way the gate voltage affects this reduction of the barrier, that is this term, that is called body factor. And the other contribution is in which way this variation of the surface potential affects the current. This term is related to the conduction mechanism in the channel, so it's related to the mechanism of conduction. In conventional devices, we have a thermoionic emission over the barrier. So again, the first term is related to a paraelectric capacitance voltage divider between the device capacitance and excited capacitance. So is given in which way the gate voltage affects the potential energy within the device is related to the capacitance, a ratio, I would say, a relation between the total device capacitance and the oxide capacitance. Whereas in which way the current is affected by the surface potential is related to the conduction mechanism. For a thermoionic emission over the barrier, this gives the famous 60 millivolt per decade value. Okay, that is the wall that fixes the ideal slope to 60 millivolt per decade. So if we have this term equal to 1, this one cannot be lower than 60 millivolt per decade. So innovative device able to break this value, that means to get that we would be able to get a lower leakage current, should do something on these two contributions. So we can reduce this paraelectric voltage capacitance voltage divider lower than 1. That is quite difficult because we have 1 plus something that in principle is positive. So in principle, we could reduce this lower than 1, or we could change, if we change the transport mechanism, we could make something on the second contribution, on this second contribution. So there are devices that have been proposed. So the ones operating on this first term are devices that are affected by what is called a positive feedback, whereas devices where we change the transport mechanism manipulate this term. So starting from this second term, because we will see we have here the most famous devices that have been proposed in the literature. We have mainly two devices that have been proposed in the literature to modify the transport mechanism. The first one is a very famous tunnel FET. The tunnel FET is a PIN device. If you have a PIN device, you have a band profile that is shown here, like this one. So what you get is that, in principle, electrons entering in the off state, electron entering the source contact, that is the P plus contact, experience that should flow in principle to the drain. The drain is an N plus contact, so electrons should come to these energies experience a barrier that is given by the band gap. So if the band gap is long and is wide, okay, the height is relatively large, so a large band gap, the current would be in principle 0. Whereas if we increase the gate voltage, we push down the bands in the channel, and what we see is that now the tunneling window seen by the carriers, the electrons entering the source, is only this yellow, I would say yellow window, okay? So we have a window of energy available for electrons entering the source to flow to the drain, in the hypothesis that they have a tunneling probability, that their tunneling probability is larger than 0 to flow from the source to the drain. So increasing the gate voltage to exponentially increase the tunneling probability at the source channel junction. So in principle, you should get a sharp transition from the off to the on state. So here, the injection mechanism, the transport mechanism is no more a thermoionic emission over the barrier, but is a band-to-band tunneling from the valence band to in the source to the conduction band in the channel. The good news, the advantages of such device is that in principle you should get a steep slope. You should get a higher on-state current at a smaller, at a VDD lower than what you need for conventional devices. The current in principle does not depend on the channel length because it is only related to the tunneling junction. So it does not depend on how long is the channel. That is very good news. And in principle should be also temperature independent. Because the tunneling window is the position of the tunneling window is related close to the Fermi level where the tunneling the Fermi distribution is almost 1, I would say. So it does not depend on the temperature in this energy window. Many, I would say, a huge number of devices, of different devices have been proposed in the literature, horizontal, vertical, with silicon, with other exotic semiconductors. A very famous paper by Alan Zibo, what showed a very famous paper is that there in the literature there are easily a wide number of devices that have been proposed that in principle from simulation should give very good results. For example, the dashed black curve are conventional CMOS. You see that all these devices in principle show a slope that is higher than the conventional one, the 60 millivolt per decade. Whereas if you move to experiments, you see that the results are not so good, I would say. Really almost bad. Some of them are really bad. You see there are devices where you are not able to switch off the device. Why? Because in tunnel FET everything depends, exponentially depends, the current exponentially depends on everything. So if there is for every small fabrication problem that you could get, for example, traps at the source to channel junction, you completely kill the tunneling mechanism. So you exponentially increase the tunneling probability, so you are no more able to switch off the device. Tunnel devices are extremely sensitive to everything. That is a bad news. Another device that has been proposed is what is called the cold source device. Oops, just one moment. This should not be here, this figure. So that is a conventional device on the left, up on left. The tunnel FET, we have almost seen the behavior of the tunnel FET. So we have electrons here, we increase the voltage and we allow electrons to tunnel throughout the barrier. In the cold source device, the idea is to filter the energy window available for electrons, not throughout this tunneling. So it's like adding a tunneling junction from the cold source to an N-type source, and then you move from here to the right. It's a conventional MOSFET, okay? And you add a cold source to filter the energy window available for electrons. So the idea is like this one. In conventional devices, you have all energies available for electrons entering the source contact, whereas in cold source devices, you have only a small energy window, that is this one, available for electrons entering the source contact. What does it mean what does it mean at the end this? So in the off state, you see, if in principle, in some way, if you operate you can do in many different ways. If you have only this yellow, I hope you see this yellow energy window available for electrons, when the barrier is higher than the maximum energy available for electrons, you have no current, okay? So you are in the off state. Whereas when you reduce the barrier, you have electrons entering the source that then travels within the device that from here to the right is a conventional device. So you have a thermoionic emission over the barrier, but you have a thermoionic emission over the barrier only until this maximum energy. Up to this energy, no electrons can enter the device. What you see that according to the energy window, that is here the gap, e.g., according to this energy window, to the thickness, to the amplitude of this energy window, you could get steeper slope in subthreshold. Other devices that have been proposed are the ones that provide a positive feedback. The most, perhaps I need to go a bit sharper, the most famous devices are the nanoelectromechanical devices, ferroelectric devices, negative capacitance devices. I will skip piezoelectric devices and I will focus on phase change devices. So in the nanoelectromechanical devices, the idea is this one. In the off state, you have a cantilever that does not short circuit the source to the drain. So the gate voltage is off, you do not have a connection between the source and the drain, the current is completely zero. Okay, when you increase the voltage in this electrode, in this actuation electrode, you pull down this beam, this cantilever, until you get a short circuit. So you experience, that are measurements, you experience an abrupt improvement of the current, because you switch on, you collapse the beam from the source to the drain. So the slope is in principle zero. The bad news are that you need relatively high voltages, and you see that you have also an hysteresis. So the voltage that you need to pull down the beam does not correspond to the voltage that you need to pull up the beam. Also, you have a movement of I would say like a cantilever. So there are also reliability problems related to stitching. After some, so the endurance is low, because after a number of cycles, you are no more able to pull up the beam. Another idea that has been proposed in the literature is shown here, and take advantage of the variation of volume that we have in phase change, using phase change materials. For example, the idea is shown here. You have a metal on the top, you have a metal here, and when the phase change material is in its crystalline phase, there is no contact between these two metals, the purple and the green one. Whereas if you if you switch the device, the phase change material to its amorphous state, the volume of this material increases until increases as much as in order to close the gap and to contact this pink contact with the green one. So you have in this way, so you take advantage of the variation of volume of the phase change material in order to get a mechanical, I would say, contact or non-contact between two metals. The reliability problems, again, you have you reduce the hysteresis and reliability improves, but still it has been proposed, it's an idea that has been proposed in the literature, but there are only few papers, but it's a promising technology in principle. In ferroelectric so in negative capacitance devices, the idea is to, since we know that in the paraelectric capacitance voltage divider, we have 1 plus the semiconductor capacitance over the oxide capacitance. If we would be able to substitute a classical oxide with an oxide able to provide a negative capacitance, here we have a negative term, so we get something that is 1 minus something. So we could get a body factor lower than 1. That is the idea of negative capacitance devices. the slope could be lower than, that is an experimental device. Again, the slope could be lower than 60 millivolt per decade. Unfortunately, again, we have an hysterectic behavior. That is a good news from, it is a bad news from a digital point of view. And also the variation, since this negative capacitance is related to ferroelectric polarization, it takes a long time to switch from polarization up to polarization down. So are almost slow devices. In the phase change based devices that are also called MOT devices, again, these devices take advantage, but from an electrical point of view and not from a volume point of view, of a variation that we have in phase change materials that is related to a variation in resistance. So this material can stay in a low resistance state and in a high resistance state. So if you put this material in series to the source contact, as shown here, if this insulator to metal transition materials, EMT material are called, if it is in the high resistive state, what you achieve is that you have a very high, let's imagine, infinite resistance, so you have no current. The current is very low. Until you get a voltage where this material changes its condition, so it moves from the amorphous to the crystalline phase. So you have a sharp transition from the low resistance, from the high resistance to the low resistance state. So you have a sharp increase of the current. Again, these are measurements, and you see that in principle you have a slope, a very sharp, very steep slope, but you need up to now relatively high voltages, and again you have hysteresis. Now I want to move to alternative information processing devices that are almost the key devices are based on spin, I would say, or magnetic field. The most famous device that has been proposed is the SpinFET. The idea is shown here. So you have two ferromagnetic materials in the source and in the drain. In the source, you have a ferromagnetic material with a fixed spin. So you inject carriers with spin up in this example. Then you have a tunneling barrier. Then you have a semiconductor, and the gate voltage is able to flip up or down the spin that you have injected. Then, so in the drain, you can get a spin up or spin down. You have a free spin material. Then you have a tunneling magnetoresistance, that is this structure. So you have a magnetic barrier, then you have again a material with a fixed spin. So the sensing is done in this way. So you inject spin up, for example, then the gate flip the spin in, spin down. If these two spins, the fixed one and the free one that you get in the drain contact, are parallel, you get a you measure a large resistance. If you get two spins that are in the anti-parallel, okay, I made a mistake. If they are parallel, you experience a small resistance. Whereas if they are anti-parallel, so spin up and spin down, you measure a large resistance. So in principle, what you measure is the variation of the resistance of this tunneling magnetoresistance. The good news of all the spin-based devices is that are non-volatile, because the spin keeps constant for a very long time. So you can get this spin down for a long time. You can take advantage of this non-volatile behavior when you design your circuit. And another major problem is that the different, it's true that you get a small resistance or a large resistance, but the difference between these two resistances is very small at room temperature. So it's very difficult to make a sensing at room temperature. Another device that has been proposed in the literature are what are called nanomagnet logic. Oh, now I see that. How long I was mute? For how long? Now? Oh, I don't know why. It changed without any information. So, do you see my screen or not? Ah, okay. So what you do is you prepare all nanomagnets in a quasi-stable equilibrium state, like the domino, and the input state of magnets causes the magnet to change from magnetic field up or magnetic field down. For example, in this majority gate, you can realize a majority gate using only 5 nanomagnets because the output is related to the polarization of the magnetic field in the input nanomagnets. The switching is very fast because you move from you pair in a quasi-stable equilibrium state, so mainly it's an unstable state in a very sharp way. But this switch is related to a dipole interaction between the nanomagnets. So this dipole interaction is very sensitive to the shape of the dipole of these nanomagnets. So there are many technology issues related to the fabrication of such devices. Last but not least, only an overview of quantum devices that are proposed for quantum computing. In quantum computing, in principle, you take advantage of a superposition of the bit 0 and 1. So you do not have a device, so the information is not or 0 or 1, but each bit can store a superposition of the bit 0 and the bit 1. So there is a probability to measure bit 0 plus a probability to measure the bit 1. There are many device concepts that have been proposed. The most famous is the superconducting qubit, so the transmon, the Josephson junction. In principle, this kind of computation would be able to perform a parallel computation on a massive scale due to this superposition, to the fact that you can store not only 0 or 1, but a superposition of the two bits. This could be used for molecule modeling, image recognition, cryptography, and communication. These are the main topics where this quantum computing devices could give a performance could achieve a huge improvement with respect to classical calculation. The bad news is that you have a large power dissipation not given by the device in itself, the qubit, but by the fact that they should up to now need to operate at cryogenic temperature, so at millikelvin, and you need to have a cryostat to keep everything at this low temperature that deliver a lot of power, dissipate a lot of power. And then you have problems related to the coherence and fidelity. So you need many physical qubits to realize an ideal one. The benchmark, just that is the conclusion. I want only to show you a benchmark between all these devices. You can benchmark these devices according to different figure of merits. For example, this graph shows the energy as a function of the delay, a very famous graph, 32-bit ALU with different devices. CMOS, so the green is CMOS, one is high performance and the other one is low voltage CMOS. Then you have the tunnel that are red, ferroelectric devices that are in yellow, others generic, exotic, I would say, and spin-based, magnetic-based devices that are all this one. Obviously, the best preferred corner is this one. Low energy, very fast calculation. What we see here is that spintronic device, then electronic charge-based ones, and usually requires higher energy in this graph. Whereas TFET, that are the red one, you see, are better than high performance CMOS in terms of energy, but they are slower in terms of delay, but are comparable, sometimes better, this one, than with respect to low voltage CMOS. Another figure of merit, we can plot here the power density as a function of the throughput density. Here, the preferred corner is this one. Obviously, very fast devices, low power, so high throughput, low power. Here, there is a constraint, so the power density, this calculation was carried out with an upper limit to the power density, this value, and you see that all the devices that are in this line, that is the limit, are on this line because we had to stop to limit the performances. We need a power density higher than this limit. So are all limited. These devices are all limited here. You see that high performance CMOS was stopped, was limited to this value. What we get is that we have seen the CMOS cannot this side, but with a higher power. This tunnel FET, that is the most promising that we have seen in the literature, that is called a thin tunnel FET because it's realized with 2D materials, with an heterojunction of 2D materials, could achieve a higher throughput than high performance with lower energy, you see. Again, spintronic devices are limited by power dissipation, are all on this line. Another point that we need to take into account are the capability of drive a load, so the interconnects that are the load capacitance. So here we plot the delay, the energy and delay of passing data through a 10 micron length interconnect. That is let's say a load fixed capacitance. In this case, obviously, if we have a huge load capacitance, the dynamic energy becomes more important than the leakage energy, and so things sometimes changes because again the preferred corner is here. That is a zoom, so that is a big graph, you see. So we have the spin-based devices that are here. We have seen a huge delay again and high energy, even with considering only the active energy. If we make a zoom in this area, that is the graph on the left, what we see that is a zoom, again, what we get is that the thin tunnel FET could achieve a delay that is lower than high performance CMOS, but with a lower energy. What we get from this graph is now that if we focus on the dynamic energy, we see that the gap with if we compare this graph with respect what we have seen 2 slides before, the gap between the charge and spin-based devices is larger because now we focus on the dynamic energy. That is even worse for spin devices. Last but not least, we can make the similar calculation benchmark by targeting not an ALU, a 32-bit ALU, but a neural network, so a different kind of calculation. So a non-Boolean computing. Obviously, digital standard CMOS devices require multiple addition and multiplication operation in order to achieve a neural network. You know that we need to make addition and multiplication. But other emerging devices could take advantage of their calculation capabilities. And what we see again, that now spintronic devices, you see, are much closer to standard high performance, to standard CMOS. Now you see that the light blue circles are almost comparable to CMOS, because they are better for such kind of calculation. And again, the TFET, for example, this one, have a significant experience, a significant, again, performance improvement due to the fact that they are able to operate at ultra low supply voltage. So if we move to a non-Boolean computing, these new exotic and new devices becomes really very, very competitive with respect to CMOS. Conclusion, so prospect and challenges. We are for sure facing many challenges related to the performance improvement and power consumption. So now low power, the key target figure of merit is energy efficiency of devices. Obviously, new physics and new device structure are proposed, are under investigation to improve, still try to improve the overall system performance. We have seen that beyond CMOS devices are based on various computational variables. So sometimes we need also to take into account that we need to perform transduction between, for example, the current, the spin, magnetic fields. We need for sure, up to now, additional fabrication improvements of these new devices that are prototypes, many times are only prototypes. For charge-based devices, we can say that the most promising up to now seems to be the tunnel FET, seems to be the leading option. For spintronic devices, we can say that they have a lower switching delay. But they are able, they have some advantages in implementing complex logic functions using a smaller number of devices. For example, if they target neural networks, they start to be competitive. And another point that we have not taken into account in the benchmark, but is very important, is that they can provide non-volatility. So that means that we could take advantage of such point. That is very important for nowadays, for example, for neural networks. So I would say that in my point of view, that is a personal point of view, a beyond CMOS device competitive against CMOS competitive in sense to replace CMOS has not been identified yet. My idea is that the future will be hybrid system where novel devices would complement CMOS devices. So my idea is that we will see hybrid systems where we will incorporate CMOS devices for conventional calculations, kind of calculation, and beyond the CMOS technologies for unconventional calculation in order to improve the overall system performance. So there is, you have seen that there is really a lot of, a huge room for improvement. There is a lot of work to do that in principle, I hope it's a good news for young researchers that there is a lot of work and a lot of fun, I would say, because if we carry out this, if we are researchers, obviously we like what we do. We like our work, so there is a lot of fun for all of us. With this, I have concluded, and I am here for questions.
Thank you, Elena, for this very interesting presentation on the future of electronics. There is one question here from Marcelo Pavanello. Thanks for the complete and well contextualized presentation. Could you please share your opinion about negative capacitance gate material and their role for MOSFET continuation?
Okay, negative capacitance. I have seen from my experience that now negative capacitance devices are more investigated, since there are also problems related to stability of this of the ferroelectric oxide. Now they are the major research application is related to they use not as for logic, for digital standard logic devices, but to realize spiking neural networks, because they provide the possibility to modulate the weight of the neural network in a quite continuous way. So they are promising devices, I would say, not for standard digital. They are in the sense that I think that they are more promising, I would say, to realize unconventional computation like neural networks. There is a huge research on that topic, and they are really very promising. Also from from experimental point of view, not only from the theoretical point of view.
Okay. You have shown several devices, non-conventional, non-charged devices. Do you is any of these non-conventional, non-charged devices that you think it's a more mature technology? I mean, we can see it commercial devices in a few years, or we are just at the beginning of this long road?
It depends, because there are devices based, for example, the spin orbit torque or the spin transfer torque. They are used already for memories, for some specific application for memories. For computation, again, for classical computation, I don't think so, but there is again, like for negative capacitance devices, spin-based devices are used again, are investigated for spiking neural networks, for non-Boolean, I would say, kind of calculations. And there are again promising results.
Okay, thank you. Let me see. There's no more questions in the chat, so I'd like to thank you again for this very nice presentation and for sharing all your knowledge with us.
Oh,
thank you.
thanks. It was a pleasure, and thank you again for the invitation. It was the kind invitation. Okay, bye.
Bye-bye. The next presentation will be in 3:20.
Thank you very much, Elena, for this nice presentation, and Henan for chairing it. So we'll have a short break, and we'll be back for the next and last presentation of the day. See ya.
Thank you. Thank you.
Okay. Hello, Andreas. Can you hear me?
Yes, I can.
Okay.
Can you hear me?
Yeah, yeah, I can. I can hear you. Okay. So,
Okay, very good.
okay.
Now, the one thing I wanted to check real quick. Oh, I see. Yes, so this should work.
Okay.
Can I share the screen for a second?
Yeah, please.
Let's just check this here. So we should be able to see this here as well.
Yeah, yeah. Okay. I'm seeing here.
Oh, okay.
Okay. For me, it's perfect. Perfect. So we still have a couple of minutes. I think we have more 5 minutes to start. So I have to say that I was impressed by your curriculum. You make so many. You work in so many places.
Oh, yeah. Yes. Actually, not that many places. In some cases, we were outsourced, so it made it from 1 to 2. So AMD and Global Foundries, where I spent most of my time, that was one place. But after that, I explored a few other places, and currently I enjoy working at Intel.
Okay. Yeah, I saw your bio and it impressed me. It impressed me really much. All very big companies, important companies. So, so I have already had some papers from yours, but it's the first time when I've met you, at least virtually. So I'm virtually glad to meet you.
So am I.
just to I have a problem with pronunciation. How do
Oh
you
no, don't
pronounce
worry.
your name? And Andreas Kepler?
Oh, it's
is it?
I go typically with Andy, but the full name is, yes, Andreas Kerber.
Oh, thank you. This was one doubt I had.
Yeah, so it's German heritage, so that's why you say Kerber in German. In English, you would say Kerber.
Yeah, I saw that it was German.
But either way is fine. I'm gonna respond to both.
Okay, thank you. So maybe you have to respond to the Portuguese accent also.
Oh yeah, I will. There's no question.
Okay. Okay. Let me see here.
So since we are up at these 3 seats, the conversation is public. Is that correct?
Sorry?
So the conversation is public, so everybody can hear what we are saying at the moment.
Yeah. Now, when we are at this place in the center of the room, everybody can hear what we are talking.
Okay.
So if we move a bit far from the center, we can talk only.
Yes,
then you can have more private conversation.
Yes, if you are on the stage but not over this blue icon, you can talk and nobody else will listen to you. only
I
those
see.
who are on stage.
Yeah.
Yeah, I don't have any this is not, I'm not a politician that I would make off the cuff remarks which would be harmful in future. So but it's the first time I enjoy a virtual conference, and I have to say this is pretty elaborate and nice. I had a, let's say, a brief session on Friday, and in order to have a conversation, somebody really had to stalk me, because I learned that unless you are in proximity and whatever the rules are, you wouldn't be able to hear. And
Yeah,
let me
that's
close the
the
window here.
metaverse.
Yes.
Well, thank you, Andy, for accepting our invitation. Oh, you're back. Well, thank you very much, Andy,
Yes.
for accepting our invitation. Well, I think we are about to start, right?
Okay, we could start.
So
Okay.
please, Rodrigo, feel free.
Okay. Could we start, Andrea?
Yes.
Okay. So first of all, I would like to thank you for accepting our invitation. It's a pleasure to have you here in this meeting, this conference. And first of all, I will make a very brief introduction about your the bio of Andreas Kerber. It's a really impressive curriculum. So, Dr. Andreas Kerber received his diploma in physics from University of Innsbruck, Austria in 2001, and a PhD in electrical engineering from the TU Darmstadt, Germany, with honors in 2014. From 1999 to 2000, he was an intern at Bell Labs in New Jersey, working on the electrical characterization of ultra-thin gate oxides. From 2001 to 2003, he was the Infineon Technologies assignee to International Simotech at IMEC, Belgium, where he was involved in electrical characterization of alternative gate dielectrics for sub-100 nanometer CMOS technologies. From 2004 to 2006, he was with the Reliability Methodology Department at Infineon Technologies in Munich, Germany, responsible for the dielectric reliability qualification of process technology transfers from of 110 and 90 nanometer memory products. During that time, he developed a low-cost, fast wafer level data acquisition setup for time-dependent dielectric breakdown testing with sub-millisecond time resolution. From 2006 to 2018, he was working for AMD and Global Foundries, both in New York, as a principal member of technical staff on front-end of line reliability research with focus on CMOS process technology. From 2018 to 2019, he was with Scorpius Technologies in Albuquerque, New Mexico, working on reliability of silicon photonic devices. From 1929 to 1921. He was with ON Semiconductor Technology in Santa Clara, California, working on product quality management of CMOS image sensors for automotive, consumer, and industrial markets. Since March 2021, he is with Intel in Santa Clara, California, working on CMOS reliability for 3D NAND technology. Dr. Kerber has contributed to more than 110 journal and conference publications and presented his work at several international conferences, including EIDM, VOSI, and IRPS. In addition, he has presented tutorials and served as a technical program committee member for several conferences such as IEDM, SDAC, Infus. Dr. Kerber is a senior member of the IEEE and a distinguished lecturer for the IEEE Electron Device Society. So after this very short introduction, please feel free to make your presentation, Dr. Kerber.
Oh, thank you for the introduction, and I'm very pleased to be here today to talk to you about the reliability of metal gate high K CMOS devices, which I worked on pretty much the entire career. Recently joining Intel and working on the CMOS in the 3D NAND technology, I'm spending more time on more conventional process technologies. As you know, this, let me see if this works here. Okay. Page down. How do I go here? Page down. Oh, this is why. Oh, here we go. Sorry for some technical difficulties. I didn't have the screen selected. So as you know, the event today is sponsored by the Electron Device Society, and their mission is to promote the excellence in the field of electron devices for the benefit of humanity. The fields of interest for EDS, there's cover a wide range of interests, going from the engineering, physics, theory, experiments and simulation to either electron or ionic devices involving all, the insulators, the metals, organic material, plasma processing, semiconductor, and also quantum effects in those materials. So it's a very wide range of interests of the EDS society. The benefit you have being an EDS member is that you have access to educational programs like today that we have these mini-colloquium or the distinguished lectures. You have publication access through the leading journals like the Transaction of Electron Devices or the Electron Device Letters. You have networking opportunities as well with the peers in the industry and academia. There are a lot of awards also given out by the EDS Society for the recognition of some of their members, and also for the students who can apply for fellowship programs. There's a lot of activity on humanitarian programs and volunteer opportunities, as well as, of course, the friendships you're gonna be able to make networking with your peers in the EDS Society. You can follow EDS on the social media. So there is a Facebook, Instagram, and also Twitter account, and you can follow activities there. And if you're not already a member today, it's a good time to join and be part of the Electron Device Society. Now, no further ado, I want to start out the lecture with some acknowledgments to my collaborators throughout the many years. Most of the work we are discussing here was carried out as part of my AMD and Global Foundries employment, and I had a lot of collaborations with reliability team members at Global Foundries who contributed to some aspects of the work we are discussing here today. Not only internal, but also we have external collaborations. Most importantly was the IBM Research Alliance, where I spent many years in New York working with colleagues there. on addressing these reliability challenges for Medgate K CMOS technologies. And as part of the membership to EMAC, we also had a fruitful collaboration with folks at EMAC as well, which I would like to acknowledge here. Just a quick disclaimer before we go into any of these the details we're going to discuss. These are the opinions, these are my opinions, which are expressed in these lectures, and they do not necessarily reflect the views of my employer, Intel Corporation. And as I mentioned, most of the data presented here in these lectures, they were all collected during the days at AMD and GlobalFoundries and can be found in various publications. Now, the motivation for this lecture is, as you know, CMOS technologies were successfully scaled basically since the introduction in the early 70s. The feature sizes were pretty large in terms of looking here at gate length in the orders of microns, tens of microns, and also in terms of the dielectric oxide separating the electrode from the MOS device channel, which were also in the order of 100 nanometer. But since the introduction of these CMOS technologies, it was successfully scaled over many generations, and virtually over 40 years, the industry succeeded in reducing feature size and scaling the technology nodes. A couple of inflection points are here when we talk about thick oxides. We are typically talking about the injection being a Faldo-Nordheim type of injection in terms of the gate oxides, and around the mid-90s, the dielectric became thin enough that we could observe a direct tunneling type of conduction through the MOS device. And the scaling really hit fundamental limits when the SiO2 dielectric virtually reached atomic scale. So these were only a few monolayer of a dielectric, and at that point, scaling in terms of scaling that gate dielectric ran out of steam and could be overcome with the introduction of a new dielectric with a higher dielectric constant, in allowing to increase the physical thickness of the film and continue to scale these CMOS technology nodes up to current. And all of that was basically guided through the scaling laws introduced by Bob Denard from IBM in the early 70s. And during my tenure at IBM, he happened to still be employed and actively contributing to the field. So I got the chance to meet Bob Denard in person, which was a privilege working within the IBM Alliance. As I said, the dielectric oxide thickness that was scaled all the way down to about the nanometer, and then a new material was introduced. And the question now from reliability perspective for reducing these feature size, that has brought a lot of challenges in terms of reliability characterization. And with the advanced nodes, these reliability challenges had to be addressed before introducing them into the CMOS manufacturing process. What were the key enablers in the last, it's not the last decades, it's basically now the last 2 decades since the 130 nanometer node, what enabled to increase the density, but also the performance for these technology nodes over the last 20 years. And basically, there are a couple of inflections starting around the 130 nanometer node, which was just a conventional dual gate oxide, dual poly, dual gate oxide, mostly a CMOS technology node. With 90 nanometer, to enhance the performance, strain engineering was introduced. And for the PMOS device, it's basically the embedded silicon germanium process, which allowed to increase the PMOS performance, but later on also for the NMOS devices, strain engineering techniques, typically liners were introduced to enhance also the NMOS device performance. So this successfully enabled scaling beyond the 90 nanometer node, all the way down to 65, with enhancements in the process, increasing concentration, for example, for the germanium devices, to get more strain in the PMOS device. On 45 nanometer again, scaling ball almost it was hit, and the introduction there of a new gate electric material with a higher dielectric constant, and the elimination of the polygate depletion effects with the introduction of the metal gate technology really enabled scaling beyond the 45 nanometer node. And ultimately, that one again, 2 generations later, led to another, challenge in the scaling going beyond 22 nanometer technology node. And there, the introduction of multi-gate devices or FinFET devices was brought successful scaling beyond the 22 nanometer node. And these FinFET device technologies, they have been scaled further from 22, I would say all the way down to currently 7 nanometer. And the next inflection there most likely is going to be the introduction of multi-sheet FET devices to scale the future generations as well. So these were the main drivers over the last 20 years enabling the CMOS technology scaling. And with the introduction of high-K metal gate, which we're going to discuss, spend most of the time today discussing the reliability challenges there and what need to be done to overcome those. Okay, so here is just a brief outline of the presentation. So we're going to first, after a brief introduction, we're going to first discuss the discrete device reliability aspects. And here we're going to focus basically on the 2 main CMOS device reliability concerns. One of them being the time-dependent dielectric breakdown mechanism, and the other one, bias temperature instability mechanism. And with the introduction of the metal gate high-K CMOS technology, we're not only focusing on the degradation of the PMOS device, now we're also going to focus on degradation in the NMOS device as well as it's going to be clear throughout the presentation. After that, in the second part, we're going to spend some time what the observations are in circuits. In here, we're going to focus basically on the characterization of ring oscillator devices and their degradation and how they link to the bias temperature instability and the hot carrier mechanism as well. And then we're just going to summarize and going to have a brief outlook what there is to expect for future technology nodes in terms of reliability challenges. Now, just to get started on the time-dependent dielectric breakdown mechanism, first, this is just a brief definition what the dielectric breakdown is and what it means to CMOS devices. So the way it is defined, basically, the dielectric breakdown, when it occurs, the dielectric is losing its insulating property, and that is reflected either in increase of the leakage current when a voltage source is applied, or a drop in the voltage across the MOS capacitor or MOSFET when a current source is applied to the gate of the device. And losing this insulating property in the dielectric is leading to failure, potential failure in CMOS circuits or in CMOS products. And the way it is handled is by a statistical analysis, because it's a statistical process. And the failure times are typically modeled using a Bible statistic. And here's just an example of an illustration what happened during such an aging test of a MOS device. So you have random defects being formed in the dielectric, and as soon as there is a conducting path between the anode and the cathode, you have the leakage increase, and at that time you count a failure of the device. And these failure times are just modeled using the statistical tools to determine the main parameters for the Weibull distributions. One of them is the beta value, which is basically the spread in the distribution, and the other one is the characteristic failure time, which is the T63 value for a Weibull distribution. The other mechanism we're going to talk about is the bias temperature instability in these CMOS devices. And as I mentioned already, with the introduction of metal gate high K into the CMOS manufacturing process, not only the PMOS device is going to suffer the instability, but now we're also going to see the NMOS device suffering an instability when the device is operated in the inversion mode. And this is basically illustrated here, moving from the conventional process, which is a polygate and oxynitride type of dielectric, moving to a metal gate high K process. You can see the instability is basically very comparable for the PMOS device. But on the NMOS side, we didn't have an issue with instabilities in the conventional poly-SON type of process, as you see here with these solid symbols. But with the introduction of the metal high K technology, you can also now see at reduced stress condition already noticeable instability in NMOS devices, and that needed to be addressed prior to introducing those technologies, those processes into the CMOS technology, the CMOS manufacturing. And here is just a simple cartoon illustrating how the gate stack looks. So in the old days, you would only have a silicon substrate and a dielectric, and then the gate electrode. But you have seen now with the introduction of metal gate high K into the CMOS manufacturing flow, this stack has gotten more complicated. In terms of high K dielectrics on silicon, you typically see an interlayer being formed in between the high K dielectric, the silicon substrate. This interlayer initially had the purpose to maintain mobility of the channel carriers. So the high K dielectric very often led to degraded mobility in the devices, but with the presence of an interlayer, an SiO2-like interface layer, carrier mobility both in N and PMOS devices recovered very rapidly. On the electrode side, in order to maintain the proper threshold of those devices, the work function of the electrode material had to be tuned, same as you do in a polyoxynitride process, where you would have N and P type topen to move the Fermi level of the electrodes to be at the right place for low threshold voltage CMOS devices. You also had to do the same now with making a proper choice of the electrode material in a metal gate high K process. So typically, N and PMOS devices have different type of metal electrodes when samples are being fabricated, and then in the replacement flow, ultimately the gate opening gets filled with a final metal material, and that one is typically the same both for the N and the PMOS device. So this is now a very typical type of gate stack cross section you would see in many of the let's say CMOS nodes since 45 nanometer, where metal high K was first introduced. Another aspect which has taken a lot of attention and time at conferences and was discussed extensively is the recovery of these bias temperature instabilities. So when the samples were stressed and then the relevant parameters were extracted, mostly looking at threshold voltage shift, you could see when samples were taken off from stress that this instability very quickly recovered, and a large fraction of the instability was reduced. And you could go through cycle by cycle stress and see this stress type buildup of the charge, and then during a recovery cycle, a relaxation and a reduction of the charge in the films. And initially it was almost like two different teams looking at the problem simultaneously. So the ones working on polyoxynitride technologies, they focused on NBTI and NBTI recovery. At the same time, also people working on metal high K technology, they were looking at the positive bias temperature instability and the recovery in those devices as well. And you can see that the kinetic looks very similar in both cases. So you have a buildup of charge during stress, and when the stress gets removed, you have a reduction due to recovery of charges in the dielectric. And cycle by cycle, you see a progressive increase, but you always see a substantial recovery. And then the goal was basically to minimize recovery effects, to make sure that worst case are being captured, and to ensure that for CMOS products, which may also operate under these worst case condition, which means almost a DC type of aging condition, that those specifications at the end are being met as well. Now, the real question is, but these are data taken on discrete devices. Ultimately, how does this impact the logic CMOS circuits? And one of them, the two main circuits to look at from that perspective is either a memory circuit, which would be SRAM devices, or on the digital side, a ring oscillator circuit. And we'll be discussing the impact on the ring oscillator circuits later on. Now, the methods to address these instabilities or the reliability challenges in general, there are two very popular methods out there. It's either applying a constant voltage and doing interim readouts of, if you're looking at TDDB, you would be just measuring the gate current, and you would sense intermittent, also the gate leakage at an operation condition. You just prolong the stress times with, let's say, a log sampling, and you monitor over the time. So in case of TDDB, you're going to have an increase in the leakage current, which you then attribute as a failure, and you use the time and the corresponding statistic to model the temperature and the voltage dependence. And the same you also basically do for the bias temperature instability mechanism. In that case, you can measure the gate current as well, but most likely you're going to focus on the drain current and so see what kind of a drain current instability you have. So in this case, you would have the gate bias reduced from stress to sense, and you would monitor then the drain current during the sense and extract a voltage shift to a time zero characteristic. And here you would look look at the time evolution as well as the voltage and the temperature dependence as well. Now, the other mechanism or the other method to characterize the mechanism is a voltage ramp stress method. Basically, you're progressively increasing the stress voltage, which let's say in layman terms would be the same as you're speeding up the aging for the device. The higher the voltage, the faster it's going to age. And you can look at either dielectric breakdown or also the device instability, and you can demonstrate that there is an equivalency with an underlying aging model between a constant voltage stress and a voltage ramp stress. And the equations correlating TDDB shown here for a power law model, as well as for the bias temperature instability, where we assume power law time evolution and also power law voltage dependence. And you can experimentally demonstrate that these two methods are equivalent. So now when CMOS technologies are going through the development cycle and into a manufacturing during the qualification, most likely you're going to see constant voltage type of stress methods being used. And this is, I think, mainly just a legacy of what JEDEC requirements are asking technology vendors to do. During the development cycles or during manufacturing monitoring, you may find these voltage stress methods being employed. And one of the reasons is that you can obtain similar data in both cases, but here you have less, you're going to spend less time during the data collection, while the constant voltage stress method can be more timely. Now, as I mentioned before, bias temperature instability recovery was seen, and there was a lot of focus on minimizing recovery effects. And for the characterization here, what is often done for bias temperature instability is you're doing a time zero characterization. Could be in the linear or in the saturation regime. You're applying the stress and you're doing only a spot readout. And the spot readout is tailored to minimize recovery effects. This time interval during the spot measurement can be in the milliseconds, or with advanced tooling, it can also be in the microseconds. So if it's in the millisecond, they call it fast. If it's in the microsecond, the term ultra fast is very frequently used, but it's basically the same characterization method. So you interrupt the stress, you read out the drain current, and either in a linear or in the saturation regime, and determine the device instability. At the end of the stress, you can also do a full characterization of the device to obtain not only the shifts, but also, let's say, subthreshold characteristics and how they degraded over the stress period, or, for example, transconductance characteristic, and compare them to the time zero data collected. Now, the operation points which are frequently used are either around the threshold of the device or in the on state of the device. And as I said, it can be either saturation or it can be linear. So linear, typically less current; saturation, you have higher currents. And from there, you can now extract either the voltage shift through interpolation to the time zero characteristic, or you can also look at current degradation. And both methods, or not both metrics, you're going to be seeing being employed. The voltage shift method is very often used for SRAM devices, where, let's say, the VT of the device is a very critical parameter in terms of stability and performance. And when you talk about aging of digital circuits, there it's not only the VT of the device, but it's really the drive current of the device, which is very critical. And in that case, you're going to see the current degradation metric very often being used. And we have done let's say, we have used both metrics depending on the applications. Another area where which has received a lot of attention in the, let's say, in the recent past, was through the introduction of the FinFET technology into the CMOS manufacturing flow. The heat conductance from the fins to the silicon substrate got degraded due to the increase in the thermal impedance with the fin devices. So self-heating was observed, and this self-heating needed to be, properly characterized. And we have taken a similar step there as well. The device, one of the device configurations we looked at was basically using heater devices to heat up the proximity the surrounding basically, and then we use a sensor device to measure the temperature. And the sensor device can either be a MOSFET, for example, or it could be a PN junction, or the sensor device could also be just a gate Kelvin probe at the various metal levels. And a very basic characterization procedure would be first to determine the sensitivity of your sensor device by changing the chuck temperature. So in the MOS device, the transistor, the threshold voltage of the transistor would change with temperature, and you can calibrate that first by doing a characterization at various chuck temperatures. And then when you turn on the heater device, you can use the change in the VT of the sensor device as a proxy for the temperature rise induced by the self-heating effect. And our observation was with the introduction of the first FinFET technology node, which was 40 nanometer in our case, there was noticeable temperature rise in the devices, but it wasn't excessive. And for any of the reliability tests, which would have a lot of current conductance during the stress, which would be basically just the hot carrier stress where the devices are in a non-state, you have a lot of dissipation. We wouldn't notice more than 30 C temperature rise in the 40 nanometer node. But of course, going to the next generation with further scaling of these CMOS devices, with these FinFET devices, you would expect a further increase in the self-heating because the thermal resistance goes up and the power density increases because you're scaling the device geometries from one node to the next one. So it is a concern to keep an eye on in future technology nodes. And of course, with the ultimate device architecture, a nanosheet, you're also going to see more of a self-heating effect and a temperature rise. So you're going to hear more about self-heating effects in these ultra-scale devices going forward. Now, this brings me to back to the outline. So in the first part, we're going to talk about the device reliability. We're going to first spend some time on the time-dependent dielectric breakdown, and in the second portion, we're going to talk about bias temperature instability. So when we started really seriously about the introduction of metal gate high K into CMOS technologies, we had to think about how are you going to compare the various process options you are exploring, and what would be really the right way of comparing them in terms of reliability. And for the time-dependent dielectric breakdown, it's basically the failure times, the T63, which is the critical parameter in the Weibull analysis. And first, we compared them with just simply the capacitance measured on the for the individual processes which were investigated. And you could see there's a very poor correlation here between failure times and capacitance of your samples, both for the NMOS but also for the PMOS devices. It's virtually uncorrelated. And the reason for that is you can achieve the same capacitance with two different choices of interlayer and high K layer thicknesses. And when you plot them now versus the leakage current, you see you get very good correlation. And the driving factor really in the failure time, TDP failure time, is not the capacitance, but it's the leakage of the device. Again, same for NMOS devices, but also for PMOS devices, the same trends are observed. And after the figure of merit was established, for subsequent node development, it became much easier to introduce the baseline and then make the proper choices in terms of processes to improve the dielectric reliability, dielectric breakdown reliability margins. Now, beside just failure time and leakage, in order to project from a small area test structure to a large area product-like structure, both the voltage dependence and also the failure distribution, the scaling from small to large areas and to low failure percentile are really the key ingredients for the breakdown projections. And first, we looked into the Poisson scaling in terms of dielectric breakdown. And in small area devices, you could actually very often see a pretty large variation, which means a shallow slope of the viable Poisson here vertically area scale Poisson distributions. But when we went to larger areas, we actually see that the breakdown distributions, they get tighter. And this was a very critical factor in order to successfully demonstrate TDDB reliability for the metal high K CMOS technology. So now from here, you basically scale still over many orders in area, because the chip areas, they are in the millimeter square and not just in the micrometer square, and to low failure fractions, which are required for time-dependent dielectric breakdown. So you have typically either 100 or maybe for automotive application in 10 parts per million failure rates to guarantee. And larger viable slope will give you more of a reliability margin compared to a shallow viable slope. The second one, with the introduction of new materials, it wasn't clear what kind of an acceleration model should be applicable. And in early 2000, power law of voltage dependence was introduced and then widely accepted in the industry as TDDB for gate oxide, voltage dependence of TDDB for gate oxide. And we did a study over many orders of magnitude in failure times, crossing a wide voltage range, also the applicability of the power law for metal high K devices. And we can confirm that, yes, indeed, metal high K follows the same power law voltage dependence as polyoxynitride devices with similar EOT values. So these two factors really enabled us to introduce metal high K successfully into CMOS technology. On the modeling front, things were taken a little further, and also the efforts made to do to come up with a percolation concept in a two-layer stack, and that was also successfully introduced, and you could show potentially different defect generation rates in the high K layer, and in the interlayer, you're going to end up naturally with a change in the viable distribution when you go from a small area device to a large area device. And the reason for that is that in a large area product-like device, ultimately, it's the random formation of defects in both layers which is going to cause the dielectric failure. So that's why you get a steeper viable slope, or a larger viable slope with a large number of tighter distribution. While in small area devices, one of the layers could be fully defective, and only the other layer would trigger the failure in the devices. So then it becomes equivalent to a very thin layer being responsible for the failure. And that's why you would get a slower viable slope or lower beta value. Now, another popular explanation was, since progressive failure were seen in polyoxynitride, that this could also be related to a progressive failure, where you basically have the formation of a failure of a breakdown spot, and this one grows over time, and that would lead to a change in the viable distribution as well. Now, since one and the other were successfully explaining, there was a third approach out there where you say you can combine the the dual layer percolation with a progressive wear out, and that will also explain the observation. But ultimately, it's really the observation, which is a tighter variable slope for larger areas, and the use for that to project towards product area, which were critical in introducing the technology into manufacturing. Now, the other mechanism is the bias temperature instability mechanism, and as I said, moving from conventional polyoxynitride to metal high K technology didn't really fundamentally alter any of it. And you have near interface hole traps or hole traps in the interlayer, hole traps in the high K layer, which could potentially cause NBTI shift, which is negative VT shift with the buildup of a positive charge. But the kinetics and the physics don't really are that difference between conventional and metal high K technology. In NMOS devices, however, it's really different because NMOS devices didn't show much of an instability when for the conventional polyoxynitride gate stack. But with the introduction of the high K layer, a lot of PBTI shift was initially observed. A lot of positive VT shift coming from electron trapping in the high K layer was observed. And it was basically attributed to defects in the upper half of the gap here, which can be very efficiently charged due to the difference in the dielectric constants between interlayer and high K layer. So the defects in the high K, they move very rapidly with gate bias. And the other one was when you went back to accumulation, so you revert from a positive VT shift to a negative, not a positive VT gate bias to a negative gate bias on the gate. You could also remove a lot of the negative charge in the film and effectively form a memory device, which would show charge trapping in inversion, and then in accumulation, you would detrap the charge. And most frequently, you're going to find now the talk about oxygen vacancies being the cause for the instability in the high K dielectric. Now, from a circuit perspective, what is the implication of the instability in those devices? And as I said, in industry, you frequently find power loss being used to model the voltage and the time dependence. So you can have now either a voltage shift or a current degradation in terms of bias temperature instability with a time evolution factor, which is typically maybe in the order of around 0.2, and a voltage dependent factor, which depending on NBTI or PBTI can be in the order of, let's say, 4 to 8 in terms of voltage dependence. So typically what was seen is a shallower voltage dependence for NBTI and a higher voltage dependence for PBTI. Now, when these devices become very small, then the instability turns into a stochastic process. So you're going to have a lot of variation in small devices, which is of concern, let's say, for SRAM circuits, which really depend on the instability of one of the 6 transistors. So in the worst case, a large array, you can have a lot of, let's say, a VT, a lot of shift in those devices because of these random fluctuation. In the digital circuits, it's more the average, because it's not just one transistor, it's a chain of transistors which forms the digital circuit. So here it's more the average of the VT shift or the current degradation, which is most relevant. So typically you would need then much less sample to study the average degradation for ring oscillator circuits, while you need a pretty large array to determine the worst case degradation for the memory circuits. Here is just an example of the bias temperature instability in these metal high K devices. So you have here PBTI on the NMOS device, and you have NBTI on the PMOS device. 2 readouts in terms of sense intervals. You have a 10 microsecond, and then you also have 2 millisecond readouts. And this would refer to, let's say, a fast versus an ultra-fast readout of the instability. You can see a small difference for the PMOS devices at short times between a fast and an ultra-fast readout. This is just further amplified here, where we just look at the differential between ultra-fast and fast, and you can see, a couple of millivolt differences between these two readouts for the PMOS device. For the NMOS device, there is very little difference you see, and so the difference is in the millivolt, or maybe up to a millivolt. Maximum here it was a 2 millivolt difference, and degradation levels in some cases being pretty significant for PBTI instability. So it's it really has very little impact. The sense interval being either fast or ultra fast for the NMOS device. So going forward, we could conclude basically that both a fast and an ultra fast, if the stress time is long enough, wouldn't have much of an impact in our long-term projections of device stability. Recovery effects in general, as I said, pretty much two teams around the same time started looking at recovery effects. And when I mean teams, it's virtually the whole reliability community, one just focusing on the conventional technologies at that time, which were polyoxynitride. So they would be looking at MBTI, and the other portion who were looking at the next generation with a focus on metal high K technologies, which were looking at PBTI. But in both cases, very similar observations were made, which is basically that after removing the stress, the instability reduces, and the reduction of the instability, first order, you can model it just with a log T dependence. So here we have the polyoxynitride case on the left, where you see to first order on the log length scale, a straight line being a log T recovery. And here we looked on our end at metal high K, so these are NMOS devices, as well with first order log T recovery. And the focus was, of course, to minimize these delay effects. So that's why the race went from 2 millisecond delays to microsecond delays. So that's why ultra-fast characterization really became the focus. A very important knob for the introduction of metal high K into CMOS technology was the scaling for the bias temperature instabilities. So in the early days of research for metal high K devices, it wasn't easy to really fabricate ultra thin high K dielectrics. And very often you're going to find literature, excuse me, thicknesses in the range of in excess of 3 nanometer, 4 nanometer, or 5 nanometer in the early days of high K development. And that would have led to a lot of instability in thicker films. Because as you can see, a real means to reduce the instability in NMOS devices was just basically scaling the dielectric thickness to 2 nanometer or less, which is the thickness nowadays used in most CMOS device fabrication. And you can, by reducing the thickness, you're able to reduce the volume, and by reducing the volume, you're able to have less defects, which can be charged. So really the most important knob was scaling high K thickness to successfully introduce it into CMOS technology. Another pretty fundamental change came with the device architecture. So previously we talked about the planar devices, and in the planar devices, with the introduction of high K dielectrics, NMOS devices show more of instability. But now with the change from a planar device to a 3D device, a FinFET device, this instability in NMOS devices is very drastically reduced. And the reason for that is basically with a fin technology, the need for a high work function material gets reduced because you can invert those at lower fields. So you get a benefit by operating those devices at lower fields compared to the planar devices. And that really drove most of the improvements on the NMOS devices. While on the PMOS device, NBTI didn't really improve. It actually got a little worse. So it nowadays NBTI is again the most pressing concern for FinFET device architectures. Beside discrete devices, looking at more circuit relevant stress mode has also become a very important aspect in the modeling of the bias temperature instability. So in the early days, it was mostly focused on DC stress and DC recovery cycles to address both stress and recovery behavior. But we spent time also to look into more digital-like operations, which is AC stress. And here, in this case, you would apply a voltage to the gate with a grounded source drain. And then you toggle the gate between a stress and 0-volt condition to mimic AC operation on the gate. Another mode of stressing, which would be more relevant to, let's say, digital circuits and also memory devices, is employing an inverter type of stress. So when the gate is stressed and source and drain are grounded in the alternate stress mode, you would bring up the drain node to the stress, and actually you ground the gate at that time. So this would be an inverter type of stress. And you can potentially see some differences in terms of the recovery behavior, whether you only alternate the gate, but you're not alternating the drain nodes. And this inverter stress, I said, would mimic basically the relaxation in SRAM devices in the cross-coupled inverter, and is directly applicable there. But it's also, relevant for ring oscillator circuits as well, and would also directly be applicable in the oscillator circuit just formed by inverter circuits. Now we have explored these AC modes in the degradation of the discrete devices. And basically the observation here was on the left, you can see here the NBTI mechanism shows typically a 50% recovery between DC stress and an AC mode. In NMOS devices, this GF here doesn't stand for global foundries. It was a gate-first planar integration scheme, and later on, most of the industry just uses a replacement metal gate scheme for FinFET devices. But you see that with a gate-first approach, where NMOS devices are very aggressively scaled, we also had noticeable recovery in PBTI. While moving to replacement technologies, the PBTI recovery diminished and is only at 10%. The stress modes can be seen here compared to DC. The AC mode shows, there's some voltage dependence on the NFET device, and also a little less recovery compared to the inverter mode. But the inverter mode, we have maybe about 20% recovery in these FinFET devices. And for the NBTI, we have independent of the AC or inverter mode. It's basically as soon as the gate moves below the Fermi, the gate voltage, the Fermi level is moved towards depletion, you have substantial recovery, and 40% of the degradation you've seen recovers from that. And it's independent now, whether only toggling the gate or also applying an inverter mode. But these recovery effects, of course, they are very relevant now for digital circuits, and we're going to see that also reflected in ring oscillators. Now, when we move from the large area device characterization, as I mentioned before, to a small device, which would be in terms of fin devices, let's say, one or several just fins. The PTI process now becomes a stochastic process. So in large devices, a lot of defects are involved in in the instability, and you see when you compare sample to sample, you have moderate variation between those. But when you go to the small devices, you can see only few defects are being now responsive for instability. And when you look across a large sample, you have a noticeable larger spread here due to the stochastic variation causing it. Now, in order to address these differences, you may need a different type of test structure configurations. So general for PTI characterization, just a simple gate, a single device is being used with a width and a length. But in reality, nobody produces nowadays a 10 micron wide FET just doing the standard characterization. So you would use multi-finger devices of narrower width devices to form a multi-finger device. But in order to address the stochastic variation in small devices, two different device configurations are now being employed. One of them is just a multi-finger stack type of structure, which mimics also a large area structure, but it has the relevant gate length. And that one can be used to determine the mean degradation very effectively without having to use a large number of samples. Or a structure where you can get both the mean and the sigma for the structure would be an array type of configuration where you can address individual devices and determine the instability of individual devices. And this is a structure we have used also to determine the mean degradation, but also the variation, stochastic variation in small devices. As I mentioned, to validate the stochastic process, you need a lot of samples. And that's, I would say, the painful part of the assessment here. Because a large sample, if you need hundreds or thousands of samples, it's not easy to accumulate stress time on a large samples if you have to do it in a sequential test mode. And the issue, of course, with the stochastic variation, that the mean of the degradation is described reasonably well by all the models, and it's only the tail of the distribution which shows noticeable differences, and that's why you need a large sample. So with a couple of hundred or maybe 1,000 samples, you can obtain on some of the shared gate device structures, you can do a 3 sigma characterization. But if you need more than 3 sigma sample size, then you have to develop a dedicated test chip to do variability characterization. And IMEC has done a lot of work in that direction, find some of their findings on using a variability test chip. One of the observation we made looking at the large sample that and the stochastic effects of bias temperature instability, that there is already some stochastic variation noted at time 0, which in the literature is not called, which is typically called random telegraph noise in the devices. And this random telegraph noise, which is there at time 0, can also impact the modeling of the PBTI and MBTI aging in small area devices, as they're present at time 0. And the question was whether they're gonna, with aging, also increase, or only the stochastic variation coming from aging is gonna be present in those devices. So decoupling RTN component from aging component, NBTI, PBTI, aging component becomes critical. And we have done an effort here to show the impact of this random telegraph noise on the PTI-induced shift. And it's most noticeable at the small amount of shift. When you don't have a lot of PTI aging, the random telegraph noise being there at time 0 can contribute, and in particular lead to skew in the tails of the distributions. but when the aging component gets large, then the RTN component typically diminishes, and you're going to see less of a deviation compared to some of the modeling aspects. And here we used, in our case, just simple normal distributions to explain the NBTI and PBTI aging. And with decoupling the RTN component, you see we have less of a deviation at technology relevant shifts. So decoupling RTN from PTI is an important aspect. Another aspect which basically drove the introduction of fin technology or FinFET technology is the time zero VT variation and how it correlates to the PTI-induced variation, which is, of course, the one for reliability perspective we are concerned about. Now, in earlier generations, time zero variation was actually pretty large, and the reason for that is since they were on bulk, the doping concentration in order to set device thresholds were pretty high, leading to a lot of random doping fluctuation in those devices. So in bulk technology here, 3228, the time zero variation is pretty large. But with the introduction now of fin technologies and reducing the doping concentration for those device architectures, you're able to really reduce the random doping fluctuation induced VT variation at time zero, both for the NMOS and the PMOS devices. Unfortunately, from a reliability perspective, the aging component with the change of the device architecture didn't really change. So they remained basically the same level of instability, variation in both planar and fin technology. Now, since fin technology had improved time zero variation, the same variation present compared to the bulk technology in terms of PTI aging makes now PTI variation a more relevant factor with the introduction of the fin technology, and something which really needs to be modeled and comprehended for both logic and memory assessment. Now this, let me just briefly summarize here the discrete device observations, and then we can move forward to addressing the circuit aspects. Now, initially we talked about TDDB failures in metal high K devices. It follows very well the Poisson scaling, which is very fundamental. And it also, with the introduction of a dual layer percolation model, the change in these failure distribution from small to large area devices could be successfully described. The aging effect, the AC effects are critical in the PTI characterization for metal high K devices, and decoupling, as I just mentioned, the RTN component from the bias temperature instability is a critical aspect when determining the statistical distribution for stochastic degradation. And an area of concern which remains is, or it keeps growing, is the self-heating effects, which we just briefly talked about. Now let me move to circuit reliability aspects, and here we're going to focus on ring oscillated degradation. We have made an effort to tailor the ring oscillator characterization in a similar fashion as the bias temperature instability, which is basically trying to minimize the time between the stress and the readout of the oscillator frequency. And this could easily be implemented with the nowadays standard parameter analysis, where you have the option of time resolved power supply switching. So we turn the power supply from stress to readout. At the same time, in our case, we turn on the divider, which brings the output signal to the scope. We can set up the scope so that the oscillation directly trigger the capture of the data. And now we are just looking at the mean frequency from the signal collected by the scope. And with the basic oscillator, the basic scope functions, like a trigger function, we can get the statistical information of the frequencies captured by the scope, which is the mean frequency, min, max, standard deviation, number of pulses on the screen, and so forth. And in addition, we can also monitor the supply currents with the SMUs to see whether we see supply current degradation and whether that also correlates to frequency degradation, or whether there are events in the supply current which would indicate a dielectric breakdown for any of the stages in the oscillator circuit. And one of the first results was to look across a different number of oscillators, different number of stages, which determines the frequency of the oscillator, and see whether there is any frequency dependence in the degradation, which was kind of suggested by some of the literature. In our case, we looked at the frequency range from a couple of 200 megahertz here to 3 gigahertz. And within the individual groups, we didn't really see much of a dispersion coming in the frequency degradation from the frequency of the oscillator itself. As I mentioned before, we can test, or actually I didn't. If I go back here, there is an enable function in many of the oscillator designs. So the enable function can either, when it's put to ground, disable oscillation. So you're going to have a static configuration in the oscillator, and it would be basically like a static NBTI or a static BBTI stress in alternating stages. Or when you put it to VDD, then the oscillator is gonna run, and the signal goes through, and it toggles and just does its desired function of being an oscillator. Now in the stress mode, you can also see we can stress them in static or dynamic. Obviously, readouts is always going to be dynamic because you have to determine the frequency of the oscillator. So, but when you see in the static mode, we typically see more of a degradation compared to the dynamic mode, and this is because in the dynamic mode you have the built-in recovery effects from both for NBTI and BBTI, while in the static mode, those are not present. And you see that in this case, there are two different process choices, two different test chips, but within the group, we always see that the static mode shows higher degradation compared to a dynamic mode. But along the different structures with different frequencies, there is no dispersion in degradation with frequency, which is consistent with what we have seen also in the discrete devices, where we change the frequencies from subhertz to maybe 50 kilohertz or 100 kilohertz. But the role of the oscillator is really to look at hot carrier degradation. So that's what the intention of the oscillator was, at least in the conventional polyoxynitride technology offerings. And it was only later with observance of NBTI degradation and the recovery where oscillators were also used. But in the older nodes, you're going to see a change in the rate of degradation of the frequency degradation when you go from a lower voltage condition to a higher voltage condition. So you see at the lower voltage condition a shallow evolution, which would be related to the NBTI mechanism, while when you go to a higher voltage condition, you see a change, an increase in the time evolution, and that would be typically attributed to hot carrier degradation, which has a time slope maybe in the range of 0.4, 0.5, or maybe 0.6. And we could demonstrate when you go to high voltage condition, you can actually see hot carrier degradation in polyoxynitride devices as well. Now, when we moved from polyoxynitride to metal high K, and at the I think, yeah, at the elevated temperature, we didn't notice that the the time evolution didn't really change, and it remains pretty shallow, but the degradation level still being very noticeable. So in the fin technology, at the high temperature, it was really the bias temperature instability which determined the frequency degradation at across the entire time and voltage range. And it's consistent with the PBTI and NBTI mechanism. We also compared the device architecture, bulk FinFETs versus SOI FinFETs. And what we notice here when we are looking at the bulk FinFETs, and we are comparing here an oscillator with 13 stages, which runs at higher frequency, compared to a longer oscillator, which runs at lower frequency. At lower frequency, you have less switching activity, so you have less this supply current, less dissipation. So you have less self-heating in a longer state, longer oscillator compared to shorter oscillator. And by comparing the higher frequency with the lower frequency oscillator and looking at the frequency degradation, we could see that in a bulk FinFET technology, we don't really see any self-heating component, even at high frequency oscillator stressed at pretty high voltage condition to decouple the hot carrier and the NBTI component. So you see at short times they're overlapping, and at long times there's a small difference, and the small difference at long times comes from the hot carrier component in the higher frequency oscillator, which is being the 13-stage oscillator. Now looking at the SOI fin architecture, here we can actually see at short stress times a noticeable difference in the degradation between the long and the short. And this difference comes now from self-heating effects. So in SOI fins, we can see self-heating component comparing a lower frequency oscillator with a higher frequency oscillator. And at long time, you can also envision here there's again a small difference coming because of the hot carrier component. And in the SOI fin, we also we carried out self-heating characterization at discrete devices. We could demonstrate that there is indeed a 4x difference in the self-heating between a bulk fin and SOI fin. And if you account this 4x difference, you can actually go back and recalculate from a PTI activation of I think 0.2 EV, what the temperature difference would have to be in order to explain. And it's the temperature rise of 30 C in the SOI fins. You may notice at high frequency, and that explains the observation here. So yes, you can see self-heating. Unfortunately, at the moment, or not unfortunately, at the moment, not in the bulk fin devices, but in the SOI fin devices at high level, high voltage stress condition, you can see this self-heating component leading to PTI differences. In addition to PTI characterization, we also used the ring oscillator to look at the dielectric breakdown. And here is just an example. In this case now, we're not employing the constant voltage method. We're using a voltage ramp method. We're looking at the supply current with increasing VDD, and also the sense out, the readout sense current in supply. In this case, since we're doing ultra fast, we're doing fast characterization for frequency measurements. We are using a fixed current range for the supply, so we can't resolve any leakage current below 10 microamp for this particular range. But you see there's no degradation in the leakage current up to high voltage, and then you see actually soft breakdown type of behavior in individual devices. Those failures very often occur before a hard breakdown in the oscillator circuits. And you can also see frequency change. The frequency change, that one throughout the sweep, that's a progressive change. up to the point where you have basically a dielectric failure. And here you can see then erratic frequency variations as well. But typically, the leakage failures occur prior to erratic frequency failures. So we use just the leakage failure to demonstrate variable distributions and the Poisson TDP process in oscillator circuits. One thing I want to notice here that actually the static degradation you see here leads to a lower failure compared to dynamic operation, and that's something which also is frequently reported now, and folks are looking into leveraging higher breakdown voltages or longer lifetimes under AC operating condition compared to a worst case static operation. And for the static operation, you see here overlaid from discrete devices, the failure times with the failure occurring in the oscillator circuit. And there's no surprise that in the oscillator circuit in static operation, it very well matches our discrete device TDDB. And in terms of ring oscillator breakdown, it is the NMOS device which limits the breakdown of that device. And you see here real excellent qualitative matching between discrete devices and oscillator failures. We also explore not just one stage, which means one area type of oscillator circuit. We look at different oscillator length, which is different area, and we could demonstrate the same points on scaling we have in the discrete devices also in the oscillator circuit across 4 different length of oscillators. It's only the largest structure which starts to deviate, and the reason for that is because in a very large oscillator structure, the current can be very significant, and a small droop in the power grid would lead to longer failure times, and that's basically what you see here, that the failure times of breakdown voltages are higher because of a droop in the grid. But other than that, the Poisson scaling known from discrete devices also applies to oscillator circuits. Now this brings me to the summary for the circuit aspects. We don't see frequency dependent, so frequency independent of BTI aging is confirmed across wide range of frequencies. So we're using the discrete devices going to sub-hertz all the way to 3 gigahertz, and we don't see a frequency dispersion in the NBTI or PBTI aging. At short stress time, it's typically and high elevated temperature, it's typically the bias temperature instability which dominates the oscillator aging. And only at particular condition you can actually demonstrate hot carrier aging components, which would be high voltage and potentially reduced ambient temperature just to get to the hot carrier aging components. Now the outlook, since the fundamentals are really strong in terms of time-dependent dielectric breakdown and also bias temperature instability, not expecting that there's going to be a lot of changes in the observation for future metal high K technologies. So there are now several nodes of FinFETs being used, and similar observations reported. There's also the FDSOI technologies which are used, and in future it's going to be the gate all around. So as long as we're not changing the channel material, similar observation are going to be also made on in future nodes. Reducing the dimension, that's just going to naturally lead to more variation, and there's going to be more focus on that as well. So we have the time zero aging, and in competition with the aging induced variation. And another area which we haven't really talked about, which is gate to contact from time dependent dielectric breakdown perspective, is also going to be an emerging failure mechanism. There's quite a bit of out there already in that area. Self-heating is a concern. It's going to be more of a concern going forward, especially with the introduction of these gate all-around structures. nanosheet or ribbon fat, however they are called, there's going to be more of a self-heating concern in those as well. And ultimately, the correlation from devices to circuit, that's a very critical area as well. And whenever we have good, whenever good correlation can be established, that helps to set the reliability trade-offs. That's all I had. If there are questions now, I would be happy to take them.
Okay. Thank you, Andreas, for this really nice presentation. It was very extensive in terms of different technologies and the effects of BTI and TDDB and of them. So the paper is now open for questions. If you have any question, please, you can write in the chat, or then you can go to the stage and open your microphone. No? Okay. While we have no other questions, I can start. So you talked about different technologies and FinFETs and planar devices. Have you had any contact with the NBTI, for example, or BTI in ultra-thin layer technologies like the UTBB transistors, for example, where we have different top gate and back gate?
Mm-hmm. You mean fully depleted SY, for example?
Yeah, fully depleted, but the one from ST Microelectronics, where we can use the back gate to
tune the VT.
Yes.
So I personally did not work on the FDSOI technologies directly, but the expectation would be whatever you would modulate the field, the interface between channel to the gate, if you modulate, and the field is really the driving factor. So if it helps you to tune the VT, to let's say reduce power consumption in one case, but to enhance in the other case the performance. Whenever you enhance the performance, I would expect you get hit with enhanced MBTI aging because you're just operating at higher field.
Okay. Thank you. Now we have a question from Professor Marcelo Pavanello from FEI. Dear Andy, thanks for the nice presentation. Are there compact model needs for BTI in FinFETs and gallium arsenide?
You mean gate all around? I mean,
all these. No. Gate all around. Sorry.
Yeah. Mm-hmm. So all these mechanisms, they're going to be covered in terms of aging simulations, and they need to be implemented in the simulator. Yes. So you have whatever time zero model cards, and you get additional model cards for the aging component, and they need to be included. Yes.
Okay. I'm seeing here. There's no more questions in the chat. So just one more question. I have worked for some time with junctionless transistors, which have it's a kind of an SOI accumulation mode device with half doping concentration. So you mentioned that the half doping concentration may affect the BTI, and also the self-heating may affect the BTI. Could you imagine a way to separate these two effects in junctionless devices, for example?
So the self-heating for the BTI should be a minor component because it's only the gate tunneling current. If you're operating in, let's say, with zero differential voltage between drain and source, so the heating should not be a big concern for those devices. If you would, let's say, drive a lot of current and a lot of dissipation, then the temperature would go up, and that makes life very complicated.
Okay. Okay. So there's no more questions. So I think we can finish here. So I'd like to thank you again for accepting our invitation, and it was a pleasure to you here at the session.
Oh yeah, thank you very much. Thank you, I appreciate it.
Okay. Now I'll just close this session. Oi. Okay.
Related to
tomorrow,
actually. Tomorrow morning we start at 10 p.m. Just to remember everyone, this is Brazilian time, so UTC -3 with the opening session. So please join us tomorrow morning. After that, we are having the first keynote speech from Professor Massimo Aliotto from the National University of Singapore. So we invite everyone to be here with us. It won't be in this auditorium, but in SBCCI auditorium that's just near the next to this one. And finally, I would like to invite everyone to visit our sponsors. There's a sponsors fair. You can visit them, talk to them, and learn a little bit more about those sponsors, right? So thank you, and we see you tomorrow. Thank you, Rodrigo.
Okay. So you have already ended this session. Thank you, Bruno. Situ.